Hello. Hi, everybody from Almeria in Spain. Welcome, everybody. Before starting, I would like to give you some technical remarks regarding the simultaneous translation. You may download the app Globenti, as you can see in the screen, in your smartphone or tablet. Entering the following code is Valmis COVID, you can see in the screen. You may select your language, use your earphone to listen to the translation through the app. So please, if you need translation, you may go ahead with this app. Okay, we are going to start with the first, my introduction. Good afternoon to those who join us from Europe and beyond. Good morning to those friends from the Americas that are accompanying us today. We have almost 1,000 people from 39 different countries joining us today, so it's an impressive number. I want to thank all for your participation in this webinar on behalf of Balmis Institute of Vaccines. The main goal for this webinar is to gather the latest knowledge and advance in COVID-19 vaccines. To this end, we have an excellent panel of speakers and researchers of different disciplines that are working in different fields, not only to discover COVID-19 vaccines, but also to facilitate distribution to prioritize countries that need them the most. Since the beginning of the pandemic, SARS-CoV-2 has infected more than 6 million people across more than 200 countries and killed almost 400,000 worldwide. So far, measures to prevent transmission and disease are based on the enforcement of the quarantine, isolation, and physical distancing. Since the first days of the pandemic, everyone has sought effective vaccines against COVID-19, which are urgently needed to reduce the enormous burden of mortality and morbidity associated with the SARS-CoV-2 infection. Developing a safe and effective COVID-19 vaccine is a global priority to end this pandemic. To date, there are 133 candidate vaccines in development worldwide. Among them, 10 have started or will soon start human clinical trials. This table shows the 10 vaccines in human clinical trials so far. There are 2 non-replicating vector vaccines. The first one from Oxford University uses non-replicating chimpanzee adenovirus as a vector, and it's been announced that it's advancing to phase 2-3. CanSino Biologics reported results of their open-label phase 1 COVID-19 vaccine trial in Wuhan, China. Their recombinant adenovirus expressing SARS-CoV-2 spike protein using adenovirus type 5 as a vector was tested in 3 doses on 188 healthy volunteers. The study published in Lancet found that most volunteers developed from both neutralizing antibody and T-cell responses to SARS-CoV-2. No serious adverse reactions were reported. 2 questions are whether responses are sustained over time and whether they correlate with clinical protection after exposure to a circulating strain of SARS-CoV-2. Other platforms use RNA technology, as does Moderna's vaccine. This company announced the trial was passing to phase 2 due to promising results, as yet unpublished. Trials were also started on Pfizer and BioNTech's RNA COVID-19 vaccine in recent weeks. Data on DNA vaccine from Inovio company have been published demonstrating immunogenicity in animal models and starting phase 1 clinical trial. So 3 inactivated COVID-19 vaccines which were manufactured by Sinovac, the Wuhan Institute of Biological Products, and the Beijing Institute of Biological Products entered clinical trials in April 2022. Finally, the company Novavax recently announced enrollment of the first participants in a phase 1-2 clinical trial of its coronavirus vaccine candidate, and a stable prefusion protein made using its nanoparticle technology and using matrix N as adjuvant. Preliminary immunogenicity and safety results from the phase 1 portion of the trial are expected in July 2020. Let me finish my introduction saying a couple of things. We are more prepared than ever in history to collaborate and find effective vaccines to combat a pandemic. And secondly, to my knowledge, it's the first time that we've faced anti-vaccination movements against a vaccine that doesn't even exist yet. Believe it or not, but it's true. Peter Hotte will tell something else about that. I would like to thank all the speakers for their support and commitment to this meeting and remind you that today we are donating funds to help the NGO Alegría Sin Fronteras in Ethiopia, supporting the vaccination program. I would like to finish inviting you to our annual meeting in Almeria in November, either online or in person. So please let me introduce you the first speakers, who is Rafael Delgado Vázquez. Rafael works as a chief of the microbiology department at University Hospital 12 de Octubre in Madrid, Spain. Rafael, you have the floor. Thanks for joining us today.
Okay. Okay, it's let me just try to share the screen. Okay. Okay. Hello, everyone. Thank you very much, Francisco, for your kind invitation. It's a pleasure. I mean, to be part of this panel of vaccines for COVID-19. And the title of my talk would be the emergence of SARS-CoV-2. What do we know so far? And I'm afraid that some of you probably will be a bit disappointed because we really don't know much. It's surprising how little, I mean, we've learned in this very, very short period. So we don't know. We still the origin of the virus is not very clear. There are aspects of the epidemiology and transmission that I mean are subject, as most of you know, of still of debate. The pathogenicity of the disease is far from clear. In other words, we don't know what are we treating. If we're treating a viral disease or an immune-mediated disease. Clinical efficacy of drugs is, I mean, it's very has not been demonstrated, and we don't really have any specific treatment that is being shown clinical efficacy. Immunology is starting to be known, but we are just in the beginning. And last but most important, we cannot completely be sure if we will have a vaccine because we have to confess that we are not very good in making vaccines for respiratory agents, and I hope that I will be a bit more optimistic at the end of this conference about this topic. The story, I mean, is well known now. I started to follow. I remember perfectly because I was on vacation at the end of the year, and I was just following an outbreak of severe pneumonia in China that remains a lot to SARS, and this is my first evidence, my first notice that a new coronavirus was related to this outbreak in the city of Wuhan in China. That was January 8th. The history of human coronavirus is described in this scheme. In blue, there are the good human coronavirus that produce between 20-30% of episodes of common colds. But in 2002, it appeared the first coronavirus that was severe, that causing severe disease. It was SARS. SARS also. It came from China. It lasted for a relatively short period of time, 7-8 months, producing around 8,000 cases, and it completely disappeared. And it was just 10 years later, in 2012, that another coronavirus producing lethal disease. In this case, it was in Arabia, and it was called MERS, the Middle East Respiratory Syndrome. That has a mortality of 30%. And then 2019, there was this new agent that it's the seventh member of the human coronavirus pathogens. This was the sequence was obtained right away, and it was clear that it was a coronavirus that was related to SARS, an homology of close to 80-85% with the SARS. And now is SARS-1, but it was very close to some coronavirus described in bats in other regions of China, with a homology of close to 96%. The genetic distance with the MERS agent is, it's farther. It's about 50%. So it's and that was the reason that this was given the name of SARS-CoV-2 due to this relationship. Most of the coronavirus are widespread in nature, and there are coronavirus for almost any species of animals, and especially mammals. The wild reservoir are bats or rodents. In the case of SARS-1, the reservoir is also bats. In the intermediate host is the civet. In the case of MERS, the origin is also bats, and the intermediate host is the dromedary camel. And most of the cases of MERS have been in relationship, in contact with infected camels in Saudi Arabia and some other near countries. In the case of the SARS-CoV-2, it's clear that the origin it's also bats, but the most close ancestor in bats is not COVID-2. So there is a step. There is this link. There is this supposed intermediate host that we don't know, and this is a piece of information that is just very, 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 very important to clarify as soon as possible. Where is this virus coming from? We don't know. We don't know yet. Just based in the first sequences of the first viruses in China and some other countries, a model of the origin of the divergence of the virus could be established, and the prediction is that the spillover, in other words, just the jump from the wild reservoir to humans, probably occur late 2019, around November. So now it's clear that there was circulation of the virus, and there were cases that were not related to the wet market in Wuhan that was initially thought that was just the origin of the epidemics. Probably the virus has been circulating not for a long time, but before that dates. SARS-CoV-2, it's a coronavirus. It's a positive stranded RNA virus that it's a big genome, and coronavirus the replication, the RNA polymerase. I mean, it's very precise. So the rate of mutation is relatively low, but the most of the viral proteins are encoded by subgenomic RNAs that are just the product of it's not a continuous transcription. The polymerase is very jumpy. It's very jumpy, so it produces a complete set of subgenomic mRNAs that encodes proteins, and that makes recombination events very frequent in coronavirus, and this is for sure part of the generation of diversity and evolution and the generation of agents that, as in this case, can jump from one species to another. As always is the case with envelope viruses, the spike, in this case, the protein that is responsible for viral entry, just captured the main attention. This is just the structure of the protein S of the spike of the coronavirus that was rapidly described, and the structure was obtained, and it was clear that it uses the same receptor of SARS-1, that is the molecule ACE2. ACE2. Here is the representation of the three-dimensional spike. Is a homotrimer, and this is the RBD, the receptor binding domain, the region of the spike that interacts with the cellular receptor. It's also very important here the region in the S protein that has to be processed by protease to prime the S protein for fusion and viral entry. And this is something special. This is something special. Here is just a more detailed scheme of the S protein. This is the RBD, and this is the receptor binding domain region. And here is the sequence of the S1 S2 junction, and it's very special because in SARS-CoV-2 there is an accumulation of polybasic, in this case arginines, amino acids, and that makes it possible to be cut by furin. And if this is something relevant for the pathogenesis of the infectivity of the SARS-CoV-2, I mean, remains to be defined. But it's a clear difference with some other coronaviruses, as SARS-1. The receptor binding domain, it's very similar to the RBD, to the RBD of the coronavirus that infects some species of pangolin. Is just pretty much the same. And there's been some speculation that the pangolin could have been the intermediate host, but it's just the RBD that is just pretty much the same, but the rest of the sequence is different, and the pangolin is not for sure the intermediate host that remains to be obtained, to be defined. From the origin of the epidemics in China, in Wuhan, the virus has is now spread to all over, and there is some variation of sequences, and some classifications have been proposed based in a relatively, here we can see some of the sites in the sequence in which mutations have been described, but still it's a relatively low number of variation. So there's been a lot of speculation if there is a particularly more virulent or more transmissible strain, but there is basically no experimental information that this is the case, and everything is based on very, very small data. We have recent information of how the infective process is done by the virus. It appears that there is a high expression of the receptor of ACE2 in epithelial cells in the nasal cavity, and it's been demonstrated that the infectivity of these ciliated cells, I mean, it's very high. And it's probably that from this initial replication in the upper respiratory way, and for mechanical reasons, the mucus material with viral particles can get access to the lower respiratory airway and to the lungs, where the most severe disease is produced. The spectrum of the clinical disease, it goes from no symptomatic at all. So it's estimated that around 30, 35%, 45% in some series of infected patients develop no symptoms at all, or very, 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 very mild symptoms. Only 10, 15% develop the severe disease, and just a small percentage, 5%, develop very, very, very very severe, mainly pneumonia with systemic inflammation and complications that sometimes are the cause of death. And it's completely different of what we knew from SARS-1. SARS-1, the onset was very, very rapid. Here, the first week of the disease symptoms are relatively mild, and it's during the second week of the disease that due to a combination that still is not completely understood of viral replication, and especially the host inflammatory response that produce a cytokine storm and a syndrome that is called adult respiratory distress, that is a very, very severe respiratory complication. Also, that sometimes it's together with the production of alterations in coagulation, producing thromboembolisms and all kind of complications that sometimes in the third week can produce the most lethal consequence that we know. Most of the infected patients develop antibodies, specific antibodies, IgM and IgG, and also IgA against the viral agent. And this is probably one of the single positive news about the virus and the disease. We know that these antibodies, especially those antibodies that are targeting the spike, the envelope spike of the virus, are neutralizing. There is a positive correlation, as you can see here, between the titer of these antibodies and neutralization. So it's possible to induce potent neutralizing antibodies against the spike. This will be covered in the next presentations, but we are starting to also to understand the cellular immune response. So there is in individuals infected with COVID-19. There are specific CD4 and CD8 T cells that are responding to different peptides or different viral products. But what is being surprising and probably should be confirmed is that unexposed individuals also have a significant percentage of CD4 and less CD8 cells that are activated by peptides of SARS-CoV-2. If this is a cross-reactivity with a common cold coronavirus remains to be defined, and if this is part of the different response of different individuals, it's also that this will be subject of investigation in the future. And this is pretty much what I like to present. So thank you very much, and I will be more than happy to answer any questions. I think that we have just a few minutes for questions now, and then at the end of the whole conference, I think that we can also have some time. So thank you very much for your attention.
Thank you, Rafael. I have some questions. One I'm going to read to a speaker. Is it your understanding that although HCOVs 229E, OC43, NL63, and HKU1 were actually identified from 1665 and 2005, they emerged into humans many centuries ago and may have caused pandemics? I cite a presentation at the Moderna TX Science Day 14th, 2020, Mark Dennison. It's a question, it's a right question. What do you think?
Well, I mean, it probably, I mean, it's likely that some of these agents have been producing much more severe disease through in ancient times. So we don't know. So probably there's been many more spillovers that we've been just completely unaware of, because they've been just occurring in the past, or they've just produced very small outbreaks that have not been characterized. But yeah, that is probably it's something that is we cannot rule out.
Rafael, there's some question about the adaptation of the virus. In many people is talking the last days about that the adaptation of the virus to humans. What do you think about?
I don't think there is any proof of that. Basically, I mean, the virus is just pretty much the same. Pretty much the same. This is based, especially I think in a different epidemiological situation, mainly in Europe now, that we are, for example, in Madrid now, the circulation of the virus, I mean, still is. It does exist, but it's much lower. And now what we are seeing in the hospitals are cases that are not acute cases, but are cases that are in evolution, and we are now seeing complications of acute infections that have occurred in the last weeks. So it's not the severe cases of severe pneumonia, but there are a lot of thrombotic and a lot of inflammation events. But it doesn't. But it's not that the virus is changed. It's that we are just We are just seeing the disease from some other perspective.
Okay, I have one question about the virus variability according to geographical areas. Is determined by environmental or human factors?
Well, a lot of sequences had been obtained, and there is a collaborative effort of many labs sending these sequences to this website, to DISAID. but still most of the variation is just based in sampling. It's just in sampling, so we don't have the whole picture, and most of the variations, and sometimes a lot of speculation have been just based in apparently the growing or an evolutive success of a specific variant, but is most of the times that more, the explanation is just sampling.
Well, there are many questions. The last one for you. Is there any explanation why SARS-CoV just disappeared after the outbreak in 2003, or was it due to herd immunity or those limited locations?
Well, no, the main reason is that the disease was completely different. Actually, it was much more severe in terms that the mortality was close to 10%, but there were not asymptomatic individuals. So it was relatively easy to identify infected patients. There were some transmission even in hospitals, but the infected individuals were so easy to identify, to isolate, to trace contacts, that was relatively easy to contain the outbreaks. Pretty much as, for example, with Ebola. Ebola is, it's too severe. It's relatively easy to identify infected individuals. Here is just completely just the opposite.
Okay, we have some question, but I think we may ask to the next speaker because are related to immunogenicity of the virus. Thank you, Rafael. Thank you.
Thank you very much. It's been a pleasure. Okay.
So let me meet the next speaker. It's Africa Gonzalez. She is an immunologist and the full professor of immunology at the University of Vigo in Spain. And she's the president of the Spanish Society for Immunology. So, Africa, thanks for joining us today. You have the floor.
Thank you very much. Thank you very much. I'm going to share my screen. I give my presentation in Spanish, but the slides are in English. The talk will be about the immune response to the virus and implications for vaccines development. So the first thing, if we want to develop a perfect vaccine, regarding the immune system, it should be safe, it will give protective immune response, and will generate long memory. For the patient, maybe they would like to have no pain, no secondary effects, maybe just to have one for several pathogens, and the idea of the universal vaccines. For governments will be to have cheap or easy distribution of the vaccines. However, for the society, our goal is global elimination from the whole earth. There are many factors that we should know that affect the immune response. The genetics, there are polymorphisms of several immune genes, HLA, the receptor itself for the virus. The age, we have seen that all people are really affected by this virus. Sex, women are presented more antibodies than men. The previous exposure to other virus similar like coronavirus or the vaccination. The virulence of mechanisms of evasion, like antigenic variations, mutations, recombinations, latency, and inhibition of the immune system, and other factors like comorbidities, other therapies, nutrition, etc. But now I will move on to Spanish. Bueno, sabemos el virus, sabemos que interacciona con el receptor AC2, que cómo se replica en el interior de la célula y comparte homología con otros coronavirus. Pero también algo muy importante es que el receptor AC2 tiene un papel en el sistema renina-angiotensina, llevando a la producción de péptidos que actúan sobre receptores que median respuestas antiinflamatorias. Estos receptores están altamente expresados durante la etapa fetal, disminuyen después del nacimiento y podría ser una de las explicaciones por la que los niños no tienen o desarrollan menor sintomatología con la infección por el SARS. Además, la infección por el SARS-CoV-2, además de una respuesta antiviral, esta disminución del receptor, del EZA2, incrementa el ratio de EZA y EZA2 y se ponen en marcha toda una serie de factores que van a afectar de forma directa o indirecta también al sistema inmunitario. Liberan citocinas proinflamatorias y también una actividad procoagulante dependiente directamente de este sistema renina-angiotensina. Por tanto, estos dos, tanto la propia respuesta antiviral como el sistema renina-angiotensina es lo que va a conferir la respuesta inmunitaria que se hace frente al virus. ¿Qué conocemos del sistema inmunitario? Que tenemos dos grandes brazos, la inmunidad innata, en la que tenemos todo un conjunto de fagocitos, células presentadoras, tenemos factores del complemento, anticuerpos naturales y células natural killer, que actúan muy pronto después de la infección, pero se sabe que hay muchos patógenos que tienen mecanismos de resistencia frente a la inmunidad innata. Sin embargo, la inmunidad adaptativa es una respuesta más tardía, pero tiene proliferación de células y, por tanto, se amplifica la respuesta. Vamos a tener anticuerpos y células efectoras. Por tanto, la respuesta va a ser mucho más potente y, además, puede generar memoria. Con respecto a la respuesta innata antiviral, las células infectadas producen interferones de tipo 1 que alertan a las células vecinas para inhibir la replicación viral. Por otra parte, tenemos fagocitos que van a mediar también en la inflamación y en la eliminación del virus. Y tenemos células natural killer que van a matar células infectadas. Con respecto a las células infectadas que producen interferón de tipo 1, lo que hacen es actuar sobre células vecinas para que inhiban la capacidad de replicación viral. En el caso del SARS, se ha visto que una temprana producción de interferón reduce el título de virus, se han hecho estudios también en modelos animales. Sin embargo, una respuesta retrasada lo que puede es mediar una respuesta inflamatoria mucho más potente. Por tanto, un tratamiento que se pensaba y que se planteaba que podía ser dar interferones de tipo alfa o beta, se vio que en algunos casos, si se daba de forma retrasada, esto era peor para los pacientes. Con respecto a los macrófagos son células que pueden ser bastante modulables, dependiendo de los estímulos que reciba, pueden dirigirse hacia un estadio de células más antiinflamatorias y de reparación, pero en presencia de interferón gamma, de factores como GM-CSF, vamos a tener macrófagos de tipo M1 con un perfil mucho más proinflamatorio. Esto se ha visto que tiene importancia porque incluso se han podido diferenciar los individuos moderados y severos con respecto a niveles de interleuquina 6 circulante que se incrementa mucho en los casos severos. Esto ha llevado a que se incluya como inmunoterapia anticuerpos monoclonales frente al receptor o bien frente a la propia citoquina interleuquina 6 o también elementos que pueden bloquear la interleuquina 1 como el anakinra, que está teniendo buenos resultados. También los neutrófilos y los monocitos se han implicado recientemente en una revisión de Nature Reviews Immunology en la participación en la formación de los trombos. Teniendo el endotelio afectado con receptores para el virus, puede haber monocitos que pongan en marcha la vía extrínseca de la coagulación y además los neutrófilos, liberando sus redes, pueden también participar en la vía de la coagulación. Y a esto se añaden infecciones adicionales que pueden tener los pacientes, sobre todo los pacientes críticos, que también tienen actividades procoagulantes, produciendo finalmente el proceso de coagulopatía y sepsis y fallo multiorgánico. Con respecto a las natural killer, son células que habitualmente están inhibidas por nuestras células diana a través de las moléculas de clase 1, pero en ocasiones las células diana pierden la expresión de clase 1 al estar infectadas por virus o desarrollarse como células tumorales. Por tanto, las células NK pueden matar a células infectadas por virus. ¿Y qué sabemos en el caso de los pacientes con COVID? Pues que el número de células NK y también de las células citotóxicas disminuye de forma muy importante en los pacientes severos. Y además, su capacidad de función está también afectada, lo que se conoce como están funcionalmente exhaustos. También se sabe que las células NK y los macrófagos podemos mejorar su respuesta. Se ha descrito hace años recientes un concepto que se conoce como inmunidad entrenada. De forma que después de una primera infección, una segunda infección, tenemos una respuesta más potente y se ha descrito tanto, como digo, para las células NK, en el que hay expansión de células, pero también hay una reprogramación epigenética de los macrófagos. Esta reprogramación está relacionada sobre todo con la condensación de la apertura de la cromatina y también la metilación de los determinados genes. De forma que cuando un macrófago es activado, la cromatina se abre y ya hay unas firmas con una baja metilación y se reestimula, este macrófago es capaz de aumentar esa expresión génica. Bueno, se ha visto que algunas vacunas, como la BCG, otros patógenos y también ayudantes de vacunas podrían activar estos cambios epigenéticos y de hecho hay ya artículos que hablan de podría la BCG usarse para proteger de la COVID-19. Con respecto a las respuestas inmunitarias específicas, estamos ya hablando de los linfocitos. Tenemos a los linfocitos helper que tienen que reconocer de forma en la superficie de células que le presentan el antígeno y estas células van a producir citoquinas que van a ayudar a otras células. Las células citotóxicas son capaces de matar directamente a células infectadas de citoquinas producidas por las células helper. Y los linfocitos van a ser capaces de diferenciarse a células plasmáticas mediante la secreción de anticuerpos. Las células T requieren presentación antigénica tanto por moléculas de clase 1, como es el caso de las células T citotóxicas. Para poder matar a la célula infectada requiere una presentación por parte de las moléculas de histocompatibilidad de clase 1, mientras que para las células helper la presentación se media por las moléculas de clase 2 del complejo principal de histocompatibilidad. El proceso hace que cuando entra un patógeno, las células dendríticas tienen que captar este antígeno, les aparecen receptores para realizar la quimiotaxis y maduran en órganos linfoides cercanos, donde van a realizar la presentación antigénica tanto a las células helper, pueden presentar también a las células que son precitotóxicas y con la presencia de interleuquina 2, estas células precitotóxicas pueden ya estar completamente activadas con sus gránulos líticos y matar a las células infectadas. También se requiere cooperación entre las células T y B para la producción de anticuerpos y para el cambio, sobre todo de clase, para producir anticuerpos que ya pueden ir circulantes para neutralizar el virus. Por tanto, las respuestas adaptativas es todo un proceso complejo en el que van a participar muchos tipos celulares y muchas colaboraciones entre unos tipos celulares y otros para finalmente tener el proceso final de destrucción de la célula infectada o de neutralización de los patógenos. Con respecto a las células T, si hablábamos también de que los macrófagos tienen una capacidad flexible, pues las células T helper, dependiendo de la activación y de qué células le está presentando el antígeno y qué citocinas se presentan, pueden diferenciarse o bien a linfocitos T helper 1, que van a producir interferón gamma, que va a ser muy importante para la eliminación de patógenos intracelulares, o bien hacia T-helper-2, muy importante para patógenos extracelulares, hacia T-helper-17, que van a participar en inflamación de tejidos y también en ciertos patógenos, y también tenemos células T reguladoras que van a medir mecanismos de tolerancia. ¿Cómo podemos modular esto? Bueno, pues también en las vacunas podemos utilizar adyuvantes que nos pueden derivar hacia un tipo de perfil de respuesta uno u otro. Las células T citotóxicas se expanden, como decíamos, los linfocitos T tienen esa capacidad de proliferación y de expandirse, se expanden, posteriormente hay una fase de contracción, pero puede haber un mantenimiento y puede haber células citotóxicas de memoria que pueden mantenerse durante mucho tiempo. Entonces, ¿cómo podemos desarrollar esa memoria inmune? Bueno, por una parte, pasando la infección y por otra, mediante la vacunación sin sufrir la enfermedad. En general, las células de memoria usualmente alcanzan sus niveles máximos aproximadamente un mes después y pueden ser mantenidas durante largos periodos. Esta memoria celular es fácilmente estudiable en el sentido de que somos capaces de que al dar después un nuevo estímulo podemos ampliar y amplificar aquellas células de memoria que se activaron inicialmente. En el caso de la memoria de las células B, tenemos por una parte plasmablastos que son de corta vida, que producen IgM, pero también tenemos cambio de isotipo a células que ya van a producir IgA, IgG u otros isotipos, y también podemos tener células plasmáticas de larga vida que pueden permanecer y producir anticuerpos durante largo tiempo. Esto se observa después de las respuestas primarias. Tenemos niveles de IgM que bajan e IgG que bajan pronto, pero en respuestas secundarias estos niveles de IgG se mantienen durante más tiempo. Los anticuerpos tienen funciones diversas. Por una parte, neutralizan el virus, pueden formar inmunocomplejos que van a ser favorecidos la fagocitosis, la internalización de estos inmunocomplejos. También algunos anticuerpos pueden activar complemento y destruir los patógenos, y las células NK en presencia de anticuerpos también dirigen sus gránulos líticos para matar a las células diana. Pero también los anticuerpos pueden dar problemas potenciales y de hecho se han visto con algunas vacunas, concretamente con algunas vacunas que se probaron con el SARS anterior. Y son los efectos dependientes de anticuerpo, que están mediados por el receptor para el FC de los anticuerpos, que lo que puede hacer es que las células se infecten aún más, incrementando también el proceso inflamatorio. Y además dan unas señales negativas a las células B vírgenes y por tanto se inhibe la activación de células nuevas, no hay activación de células raíz. ¿Y qué sabemos sobre la protección de anticuerpos? Bueno, pues en datos ya del año 85, en voluntarios infectados se vio que los anticuerpos frente a este coronavirus disminuían muy rápidamente, ya a las 12 semanas, y eran muy bajos a los 12 meses. Con la infección natural, en este mismo artículo, se veía mayor variabilidad, pero en torno a los 6 a los 12 meses era el tiempo que se mantenían los anticuerpos en estos individuos. ¿Y qué sabemos de los anticuerpos frente al SARS? Pues la infección natural, en este artículo que he visto con 338 pacientes, se ve que tanto pacientes con enfermedad moderada, severa o crítica tienen anticuerpos. Sin embargo, si nos vamos a artículos recientes del grupo del Instituto Pasteur realizado en 160 personas de staff, detectan que por 2 ensayos un alto nivel de positividad y que muchos de ellos tienen anticuerpos neutralizantes, como decía anteriormente el doctor Delgado, el 98% ya a los 28-41 días tienen anticuerpos neutralizantes. Sin embargo, el grupo de Michael Nussen en Estados Unidos, en 149 pacientes convalecientes, encontró niveles indetectables a los 39 días, por debajo de 1000 el 79% y títulos mayores de 1,5000 solamente en el 1%. Sin embargo, indica en el artículo que encontraron anticuerpos específicos frente al RBD con potente actividad antiviral en todos los individuos testados. Lo que pasa es que a títulos bajos. Estos resultados contradictorios en la serorelevancia, hay bastantes problemas que se han detectado. Por una parte, hay una gran variedad de test, algunos con distintas proteínas, algunos incluyen la proteína S, otros la N, incluso algunas empresas no indican ni siquiera el antígeno. Algunos de ellos se han visto que no son muy específicos y que también dan croreacción. También se han estudiado a distintos tiempos, algunos han estudiado IgM, IgG, otros han estudiado anticuerpos totales, otros han incluido la IgA y también se ha visto croreacción con otros coronavirus. Hay también ELISAs y quimioluminiscencias, tanto comerciales como in-house, y también se han visto diferencias con respecto a estos ensayos. Con respecto a la croreacción de anticuerpos, se sabe que hay croreacción. Ya en el artículo del año 85 hablaban de croreacción entre varios coronavirus. También en el año 2012, entre el coronavirus EMC con coronavirus de los catarro común, y recientemente, en el 2020, se ha visto también respuesta de anticuerpos croreactivos entre el SARS-CoV-2 y las infecciones del anterior SARS-CoV, pero dirigidos frente a la proteína Spike, aunque la mayoría de ellos no neutralizan la infección, es decir, estarían pues dirigidos frente a otras partes de la molécula. Ya, tal como ha mostrado previamente el doctor Delgado, uno de los artículos recientes en Cell muestra que no solo los pacientes infectados por COVID, pues el 100% desarrollaron anticuerpos IgGs y 80% IgAs frente a la proteína S, sino que los linfocitos CD4 y CD8 reconocían distintas partes de la molécula y a nivel de CD8 menos que de CD4, que son las células citotóxicas, pero que reconocían antígenos en estas distintas estructuras. Y que individuos no expuestos, eran células que tenían congeladas entre los años 2015 y 2018, por tanto antes de la entrada del SARS-CoV-2, que el 50% de las personas tenían células CD4 positivas que reconocían al virus y un 20% de células CD8. Ellos estimaban que podía ser por croreacción con otros coronavirus, pero este dato no lo podían confirmar, solamente por datos epidemiológicos. Otra cosa importante que tenemos que tener en cuenta cuando queremos desarrollar una vacuna es el nivel de respuesta inmune que queremos obtener. Y siempre las mejores respuestas van a ser cuanto más similar sea al patógeno original. Por tanto, cuando utilizamos un patógeno atenuado, obtenemos tanto anticuerpos, memoria B, células helper, células de memoria y células citotóxicas. Si ya trabajamos con patógenos muertos, donde no hay replicación en el citoplasma y no hay presentación antigénica a las células T, podemos perder esta memoria. También, si no hay persistencia del antígeno, se perdería la presencia de anticuerpos, y lo mismo si solamente se utilizan antígenos internos, no tendríamos ni anticuerpos, ni células de memoria, ni células citotóxicas. Esto hay que tenerlo muy en cuenta para el desarrollo de las vacunas. Y otro elemento muy importante que antes también comentaba, que es ayudar a dirigir la respuesta de los linfocitos T, son los mecanismos de acción que tienen los adyuvantes. Algunos de ellos tienen un efecto de pod, el permitir un acúmulo del antígeno y que se libere lentamente, como es lo que hace el alum, o también el MF59, que es una emulsión de escualeno en agua. Pues si queremos una respuesta más de tipo TH2, podríamos utilizar el alum, pero si queremos una respuesta mixta, podríamos utilizar otro. También podemos utilizar activadores del sistema inmunitario, como los elementos que tocan los toll-like receptors y que van a activar, por ejemplo, células T citotóxicas, respuestas mixtas de TH1, TH2. También la activación del inflamasoma a través de NLR3 o ayudar en la presentación antigénica como hace el escualeno. Estos elementos hay que tenerlos en cuenta cuando se trabaja con una vacuna. Por lo tanto, si queremos hacer una vacuna, primero tenemos que ver el antígeno, si vamos a trabajar con el virus completo, con subunidades, proteínas, ácidos RNA, y cuanto más similar sea para el virus original, mejores respuestas se esperan. El tipo de respuesta inmune que queremos, si es más de tipo anticuerpos, TH2, si queremos más dar a la citotoxicidad o si queremos una respuesta mixta. Los ayudantes nos pueden ayudar a dirigir esas respuestas. ¿Y qué componentes deberíamos de incluir en la vacuna? Pues tal como describen en este artículo en Cell, dado que los linfocitos y sobre todo los citotóxicos van a ser los que finalmente destruyan las células infectadas, se deberían de incluir no solo componentes de la proteína S, sino también componentes como el M, el N y el NSP. También hay grupos que están haciendo predicción de qué epítopes del virus son los que mejor se expresan en las moléculas de histocompatibilidad de clase 1, como el grupo del doctor Tony Rivas en Estados Unidos, porque va a ser importante para la activación de las células CD8. Y no podemos olvidar el efecto también de la activación de la memoria entrenada y clásica, porque vamos a tener una potenciación de la memoria T con la memoria de las células NK y de los macrófagos potenciando ambos brazos. Y nada más, esto es, muchas gracias por su atención y nada, si tenéis alguna pregunta, tanto en castellano o en inglés, pues sin problema.
Thanks, África. Tenemos muchas preguntas. Voy a traducir una aquí desde el punto de vista clínico. ¿Qué datos podrían ser usados para cuantificar la calidad y la cantidad de respuesta de las células CD4 y CD8?
A ver, uno de los primeros problemas es que necesitamos estándares y, por ejemplo, no hay todavía ni siquiera estándares internacionales para los ensayos de anticuerpos. Por tanto, la mayor parte de los ensayos de anticuerpos se están haciendo utilizando estándares internos, pero no hay un estándar internacional. Y este es otro de los problemas. Lo que se está haciendo, y sobre todo en las publicaciones científicas, es esa comparativa entre qué está ocurriendo con los pacientes, con las personas normales, con las personas que están con enfermedad leve y enfermedad grave, haciendo una comparativa entre ellos. Realmente un estándar internacional de este tipo de respuesta ahora mismo no la tenemos.
Hay una pregunta: ¿qué proporción de pacientes desarrollan anticuerpos protectores y si es posible la reinfección?
En el caso de lo que se está observando en los pacientes, en los sanitarios, tanto los datos que ha presentado el doctor Delgado como los mostrados en algunas de las publicaciones, indica que la mayoría de las personas que han pasado la infección desarrollan anticuerpos. Y tanto los que lo desarrollan leve, moderado y severo como lo que he presentado en la exposición. ¿Cuánto tiempo duran esos anticuerpos? Es algo que ahora mismo no lo sabemos. Sabemos los datos, sobre todo de China, que sí que duran durante todos estos meses, y tenemos los datos de los otros coronavirus y del SARS y el MERS. En el caso del SARS y el MERS se detectaron anticuerpos hasta pasados 2-3 años. No sabemos cuánto tiempo van a durar estos anticuerpos. Con respecto a las tasas de reinfección, los datos que hay ahora mismo en España es que los casos de reinfección son muy, muy bajos. Creo que no llegan al 3% de personas que vuelven al hospital o al centro de salud como consecuencia de la infección. Si estos son reinfecciones o que el virus seguía persistiendo y que algunas de las técnicas de PCR dieron negativo, eso habrá que verlo. Pero realmente casos de reinfección son anecdóticos.
Ok, por último, dejaremos más preguntas para el final, pero ¿qué relevancia tiene el hecho de que personas no expuestas tengan capacidad de respuesta al SARS-CoV-2?
Hay que demostrar que esas personas que estuvieron expuestas a coronavirus del catarro común, realmente esos anticuerpos y esos linfocitos, que no tenemos que olvidar siempre cuando hablamos de inmunidad, que no son solo los anticuerpos, sino también los linfocitos, que realmente les proteja de esta infección. Eso ahora mismo no está demostrado, que realmente haya una protección del SARS. Sí que sabemos, y esto es muy buenas noticias, es que el 85% de las personas infectadas, su sistema inmunitario es capaz de resolver la infección de forma o bien asintomática, aproximadamente un 30-35%, o de forma leve. Y eso es algo que tenemos que transmitir porque, aunque es una infección que produce letalidad y enfermedad grave, el 85% de las personas, su sistema inmunitario lo va a cubrir adecuadamente.
Okay, thanks, Africa. We'll have more questions at the end. Let me introduce to Dr. Peter Hotet. Peter, are you there? Peter, are you connected?
Yes, I'm here.
Okay. Hi, Peter. How are
How are
you?
you? Nice to see you, Doctor.
Nice to see you,
Thank you
Peter.
for having me.
Let me introduce you. Peter Hotet is the Dean of the National School of Tropical Medicine at Baylor College of Medicine. He's professor of the departments of Pediatrics and Molecular Virology and Microbiology at Baylor College of Medicine. He holds the endowed chair in tropical pediatrics at Texas Children's Hospital, as well as being the co-director of Texas Children's Hospital Center for Vaccine Development. Peter, thanks for joining us today. You have the floor. Thank you.
Thank you, Doctor. It's a real honor to be reconnected with the Balmis Institute. I've really enjoyed my association with Balmis, and congratulations on all the great work that you're doing. I apologize for not giving my lecture in Spanish. The last time I tried to do that, my oldest daughter was with me in the audience, who speaks very good Spanish, and I asked her how she thought I did, and she said, "Daddy, please promise me you'll never embarrass the family again by speaking in Spanish." So I've been traumatized by that, and therefore I will, along those lines, continue in English. But my heart is in Spanish. I will. Looking for the presentation now. Hold on. Just make certain here. Is everybody there?
Yes, we're here.
Okay, great. Here we go.
Here we go. You need to share your screen.
Yes, do you see it now?
Yes.
Okay.
Have the floor.
I'm still, even at this late date, I'm still learning all my new COVID technologies. Can everybody see, can you see this okay now?
Yeah, we are seeing you very well.
Oh, good. So, well, thank you. So I'm going to give a pretty broad overview about not only COVID-19 vaccines, but in the larger context of global health. I enjoy writing books, and my next book that'll come out at the end of this year has this title, Developing a Vaccine against Pandemic Threats in an Age of Anti-Science, which includes COVID-19. This is a new free book that you can download if you go to Johns Hopkins University Press Project Muse, they, in addition to the book coming out next year, they've just done now an instant book version of a previous book called Blue Marble Health, and we've now updated it to reflect the current situation in COVID-19, particularly around the fact that COVID-19 for many countries, including the United States, it's really emerging as a health disparity, more among the poor than any other population. And this concept of blue marble health has to do with the fact when you add up many diseases, not just COVID-19, but many of the neglected tropical diseases, they're disproportionately occurring among the poor living in wealthy countries. And now we're starting to see this disease accelerate dramatically in Brazil, and now Iran is having a recurrence, and we're projecting huge numbers of cases in India. So this is going to be a new frontier for COVID-19 as it passes through what we call the global south, meaning places like Brazil and India, which are still G20 countries, but the poor living among G20 countries. And that's why this is called poverty and the impact of COVID-19. Now, as many physicians know all too well in Spain right now that and elsewhere, that both the original SARS in 2003 and now the COVID-19 virus, SARS-CoV-2, bind very tightly to the ACE2 receptor, which is the angiotensin converting enzyme, and carboxypeptidase. And this has been associated with lots of vascular effects. So here in the United States, we're starting to see a very high rate of coagulation disorders and thrombotic events, leading to pulmonary emboli, stroke, and coronary thrombosis. And we think a lot of this is due to this very tight binding of the COVID-19 virus to the ACE2 receptor. The first virus did it as well, but not as tightly. And this is a recent summary of the tissue expression of the ACE2 receptors in the heart and in the blood vessels. So increasingly, we're thinking of COVID-19 as a vascular event, and of course the lungs, but also adipose tissue, which may reflect the finding that obesity and high BMI, body mass index, is an important risk factor for COVID-19. We're now starting to project of what happens in COVID-19 after this initial wave of infection. And these are some results from Mark Lipsich's group at Harvard School of Public Health, suggesting that their models are seeing an annual seasonal wave in the Northern Hemisphere, big peaks in January, February. So as terrible as this year has been, the concern is now where we may be able to expect yet another big wave come January, February. And this really does highlight the importance of developing safe and effective vaccines. Now, almost all of the vaccines that are now being developed operate more or less against the same principle, and that is to create an immune response against the spike protein in order to prevent the attachment of the virus to our host tissues. And in particular, now the emerging evidence is showing it's not just creating an immune response against the spike protein, but creating high titers of virus neutralizing antibody. That's going to be especially important. And we saw this in our work with the first SARS coronavirus vaccine. We needed high titers of neutralizing antibody. And now Dan Baruch's lab at Harvard Medical School and Beth Israel Deaconess has more or less shown the same thing. So the question then is, what's the best way to achieve high titers of virus neutralizing antibody in a vaccine? And on the left is a recent slide taken from Dr. Anthony Fauci, I'm sure many of you know, looking at the different types of technologies ranging from nanoparticle technologies, recombinant protein technologies like what we're doing, live attenuated viruses, virus vector platforms like adenovirus, Johnson & Johnson and the Oxford vaccine, also DNA and RNA vaccines like we're hearing about from Moderna and CureVac from others, but essentially they're all working to see which one can create the best immune response against the spike protein, in particular, what might achieve the highest level of virus neutralizing antibody. And our vaccine approach is a bit different in that we're very much focused on the global health problem of COVID-19. As I mentioned, what's happening in Brazil, in India, and really as this virus races through the global south and causes really a humanitarian catastrophe. So what we've done now is our group, Texas Children's Hospital, which is the Texas Children's Hospital Center for Vaccine Development, part of our National School of Tropical Medicine, has created now a global coronavirus vaccine initiative jointly with this organization here known as PATH. That acronym used to stand for the Program for Appropriate Technology in Health. And now they basically just go by the name of PATH. And they're a very important Seattle-based organization that's worked very closely in the past with the Bill and Melinda Gates Foundation. They led the acceleration of the malaria vaccine for Africa and the meningococcal A vaccine for Africa. And now they're working with us. So our Texas Children's Center for Vaccine Development, CVD, our approach is to develop low-cost global health vaccines. These are recombinant protein vaccines that actually works on doing technology transfer to low and middle income countries. So we like to do vaccine development capacity building. And our approach is to use technologies that are actually underway in many middle income countries. So a lot of our vaccines, like the portfolio on the right, mostly around parasitic infections like schistosomiasis and river blindness and leishmaniasis, focus on using Pichia expression systems. This is a yeast expression system, which is the same used to make the recombinant hepatitis B vaccine in places like India and Brazil. And we're using the same approach for our coronavirus vaccine program that we took on about a decade ago. So we're actually not virologists. We work mostly on parasitic diseases. But a decade ago, nobody cared about coronavirus infections, and we adopted this, partnering with this wonderful group at the New York Blood Center listed here that had pioneered the development of a lot of recombinant coronavirus vaccines. And our big concern, of course, is what's happening as this virus races through the favelas of the Brazilian cities and the crowded urban areas of India and Africa. We envision a terrible humanitarian catastrophe. We've seen this, of course, in Guayaquil in Ecuador. Could we accelerate a vaccine that specifically targets these groups? And with that in mind, our first vaccine that we were developing two vaccines. One is we already have manufactured a recombinant protein vaccine made against SARS-1 that we think we can cross-protect against SARS-2. And now we have a second candidate, one that's specific for SARS-2, and they're both pretty similar. They're both expressed in yeast, give high levels of expression. And this is a modified protein, and for both SARS-1 and SARS-2 protein candidate, which we call RBD219. We call it N1 because we found by removing the N-terminal amino acid, we removed a lot of the excessive glycosylation. So it was much more amenable to scale up production. These are some of examples of in our mouse studies working with Ken Cheng at UTMB Galveston, the Galveston National Laboratory, using a transgenic mouse model, mice genetically modified to express the ACE2 receptor. We're getting very high both endpoint IgG titers and also high titers of neutralizing antibodies as well in our mouse system. So we're very, and we can do this either with a pseudovirus or do this with a live virus. And what we're achieving is high levels of survival compared to the control mice. We're getting 100% survival compared to 0 survival in the control, and we can evaluate different constructs as well. And we do a lot of work also to avoid this problem that we heard about previously, this problem of immunopathology. And one of the things that we're observing with immunopathology, people just call it all antibody-dependent enhancement. In fact, what we do is we separate the two forms. We think the bigger problem is what we call eosinophilic immune enhancement. These are cellular infiltrates in the lung and liver upon virus challenge, particularly with some of the virus vectored vaccines. And we actually find that alum reduces eosinophilic immune enhancement. So you're sometimes hearing, because there's eosinophils, it must be a Th2 response, but in fact, we're finding it more linked with IL-6 and a Th17 response, which also can have a prominent eosinophilic component. And the antibody-dependent enhancement is observed in vitro with some viruses, including coronaviruses, and there's differing opinions whether it's due to neutralizing antibody versus non-neutralizing antibody, but we're not really seeing that so much as the former one, the eosinophilic immune enhancement. And here's an example of what it looks like. This is an immunohistochemistry staining with looking for eosinophils, and the brown dots is an eosinophil, and you can see with the full spike protein, we see quite a bit of eosinophilic immune enhancement, not so much with the receptor binding domain on alum. So we're pretty excited about moving this forward. And now, in collaboration with Lan Yingdu's lab, she has shown that the antibody to our vaccine cross-reacts with the SARS-CoV-2 receptor binding domain and S protein. So it gives us some optimism that we could get cross-protection. Now, before I end, the other thing we're very worried about is some of the language being used to accelerate the vaccine initiative in the United States, because one of the big problems that we have in the US is a very aggressive anti-vaccine lobby that began more than 20 years ago, but it's accelerated in recent years. And the reason that's relevant is the White House is now calling our US vaccine program Operation Warp Speed. And that may sound attractive because it means we're rapidly progressing, but the problem is the anti-vaccine movement, what they allege, of course, is that vaccines cause autism, and I've spent a lot of years in my life debunking that because I have a daughter with autism. And the last time I spoke at the Balmus Institute, I talked about my book, Vaccines Did Not Cause Rachel's Autism, to combat the anti-vaccine movement. But now, because of some of this Operation Warp Speed language, what we're seeing now is a significant number of Americans in the US will refuse to take the COVID-19 vaccine, even if it's made available. And again, this is all due to the anti-vaccine lobby. So this is part of a larger anti-science movement we're starting to see in the United States. And unfortunately, it's particularly strong in Texas, where I live and work. We have great scientists, great scientific institutions, but we also have a pretty aggressive anti-science movement. So in fact, even today, because I'm on social media, on Twitter, I'm being attacked by a prominent lawyer in Houston, spouting anti-science sentiments. So this is very real and it's very concerning. They don't only go after me, they go after, of course, Dr. Fauci and Bill Gates and Dr. Birx, and the list goes on, but it's a very concerning trend. And this is part of what the World Health Organization recognized in 2019. They listed vaccine hesitancy for the first time as one of the major global health threats in response to the fact that there were more than 100,000 measles cases in 2019, and now it's spilling over into COVID-19 language. So these are the number of kids in Texas who are denied access to vaccines. We're now up to about 64,000 kids, and the number's going higher. So we're reaching the point where we have 100,000 kids not getting their vaccines in the state of Texas. And it's linked very much to not only the anti-vaccine movement, but now they're spilling into misinformation about potential COVID-19 vaccines. So we're very worried for that. And now we're starting to see steep declines in measles, mumps vaccine coverage in the United States. I'm sorry for the misspelling there. But especially with the lockdown, we've had a steep decline, and I'm worried that it may not come back accordingly, because we're not, so we're at the risk now of seeing this co-endemic situation where we not only have to worry about COVID-19, but also return of measles and now, of course, influenza, because many Americans are not getting their influenza vaccine. So I'm quite worried as we see repeated rounds of COVID-19 in the coming years. And this is why I've been devoted a lot of my life to this concept of vaccine diplomacy, that is not only working about what vaccines we're developing, but how we can co-develop vaccines with other nations. And it's an idea that inspired me. I was inspired by Dr. Albert Sabin, who developed the oral polio vaccine jointly with the Soviets at the height of the Cold War. Two countries putting aside their ideologies to work together to make vaccines. And I think this is what we have to pursue for our COVID-19 vaccines. I'm very concerned about this new nationalism we're seeing around vaccines. You're hearing about the Chinese vaccine, or the American vaccine, or the European vaccine, or the British vaccine. This is terrible, I think. In fact, there's even a new term that's been developed called vaccinationalism, and it has no place. We have to pursue vaccine diplomacy to ensure that all of the world has access to not only COVID-19 vaccines, but vaccines globally. So I see the coming, this is my last slide, I see the future as a bit of an epic struggle between having vaccines, but also all of these new 21st century forces like anti-science, but also poverty, climate change, war, political collapse, and urbanization. So I'll stop there and see if we have time for questions, and I'm certainly happy to take questions.
Thanks, Peter. Thanks, excellent presentation. We have some question. Do you think because everyone has been under time pressure, single antigen S approach had dominated by vaccine research? Either we will need a multi-antigen approach, example M, N, and N's?
That's a very good, it's an excellent question. And, you know, sometimes I worry we overthink this problem a bit. When I look at right now, I mean, we have our recombinant protein vaccine, and I'm enthusiastic about that. But when I look at one of the best vaccines that I'm seeing so far in non-human primates is the Sinovac biotech vaccine from China. It's very old school. It's an inactivated virus vaccine. It's the SARS-CoV-2 grown up, purified, and then inactivated with beta-propionolactone and then alum adjuvanted. It's about as old school as you get, and yet it's a very effective vaccine. I don't know what the safety profile will be, but you know, it's really interesting that sometimes, you know, we're so precise, and we put so much molecular biology and some of the best immunologists on a problem. I often worry sometimes we overthink it. You know, look at what Jonas Salk did, or Sabin did, or the measles vaccine. But we'll see. We'll collect that information, and you know, this is an exciting time because we'll get so much information on so many different technologies at the same time.
Mm-hmm. Someone is asking you about if Texas has any plan to contract with the wave for anti-vaccination wave.
Yeah, things are very bad in Texas right now. We have an aggressive anti-vaccine lobby, and what's happened in Texas is quite interesting. It's now, starting in 2015, they started to align themselves with the far political right. And, you know, we have something in Texas called the Tea Party, which is like a libertarian party, believes no government interference. And now what they're doing is it's not only saying not to vaccinate, but they're also saying you cannot tell us to do social distancing. We're not going to allow contact tracing because that violates our freedom and our independence. And it's got a lot of strength. They've got money, they've got power. So I do worry about it. And so there is this, you know, the United States is a very interesting country. We have some of the best research institutes and universities in the world, but yet we also have some of the most aggressive anti-science movements in the world as well. And the two are conflicting and coming head to head, particularly in Texas. And it's made life very interesting for me. Now they've given me a new name. They call me the original gangster villain. So that's my new name in Texas and nationally. And what can I say? Fighting anti-science movements, unfortunately, is going to go hand in hand with being a vaccine scientist. And we just have to be very outspoken as scientists. I think it's really important that the public in general gets to see the face of scientists and physicians, because just being invisible will only strengthen anti-science movements.
Yeah. I said in my introduction that, to my knowledge, it's the first time that we face anti-vaccination movements against a vaccine that doesn't even exist yet.
That's right. That's right.
It's the first time in history.
But we're making it worse because we have, by calling it Operation Warp Speed, that's created a problem. That was a really dumb thing to do, to call it Operation Warp Speed, because it plays right into the hands of the anti-vaccine movement. Or, and also we've had some problems with some of the biotechs around inside stock trading and dumping stock and conflicts of interest. And again, what the anti-vaccine lobby claims, they say there's all this dark money behind vaccines, and and it plays right into it. So we've created our own problem by strengthening the anti-vaccine movement.
Okay, last question. Did you find antigen variation in SARS-CoV-2 that could prevent the durability or the efficacy of the effect of the vaccine along the years?
As the question, what's the durability of of immunity? We don't know. If it's a new virus, we've not even been through this a full year. When you looked at the convalescent patients with SARS-1, they had persistent antibody for at least 2 years, and some say up to 12. And even then, there might have been memory B cells around. So hopefully it'll be like that situation. But we don't know. I think we're not going to know about the need for boosters and things like that until we follow this vaccine for many years. And this is going to be really important. If we're going to be successful in a global vaccine program, we're going to have to communicate with the public a lot. First of all, there's going to be not just one vaccine. There may be 4 or 5 different vaccines for different age groups, different technologies. Some may need a booster, some won't need a booster, some may need multiple boosters, some may have different safety issues. How we're going to orchestrate that is going to be very not easy. We're going to have a lot of communication. So we're going to need really good people trained in vaccine communication and policy. There's going to be a real need for that in the coming years.
Well, last one. Do the SARS-CoV-2 vaccines will necessarily be adjuvanted? Adjuvant?
Adjuvanted? So far, I don't know. Certainly our recombinant protein vaccine, we do not get protection unless we adjuvant. And the inactivated virus vaccine's the same. The mRNA and the DNA vaccines, they're not really adjuvanted. It's just that they are processed in a way. It's not just the DNA and RNA. They're in a lipid envelope, so they're encased, right? So in a sense, that's a form of adjuvantation. So I think most of the vaccines probably will need some type of adjuvant, maybe not the live virus vaccines. And these may be very good as well. I'm pretty excited about some of the vaccines Merck and companies developing. They have a VSV vaccine, which is the same technology used for the Ebola vaccine, as well as this attenuated measles vaccine that was developed at Pasteur, Institut Pasteur, and now then with a biotech company named Themis. And I'm quite enthusiastic about that as well.
Okay. Thanks, Peter. Thanks for joining us today. Thanks for staying here today.
Thank you very much. I may stay for a little while. And again, congratulations on the conference, and congratulations to all the great work of the Balmus Institute. What you're doing is so important to get the word out about not only what vaccines are, but vaccine safety, and you're doing very important work, and very grateful for having me.
Hope to see you soon in Spain.
Yes, I hope so. Bye-bye.
Bye. So let me introduce to the next speaker is Martin Bachmann. He's head of the Department of Immunology at Bern. He's professor of immunology at University of Bern, associated professor of immunology at the University of Oxford, and visiting professor at the University of Zurich, and he sits on the scientific advisory board of a number of companies. Martin, thanks for joining us today. You have the floor.
Thank you very much for this kind introduction, and thank all of you for listening to me. And can you see my slide?
Yes, perfectly.
Just as a little disclaimer, I am professor in Oxford at the Jenner Institute, but I have nothing to do with the vaccine they make at the Jenner. So don't mix that up. So just a reason why we still need a vaccine is I just basically would like to point out one number here. So in China, this COVID-19 disease is still under control. But if the numbers are correct, 99.99% of the Chinese are still susceptible. And even if the number of cases they gave us are wrong by a factor of 100, it's still 99% of them susceptible. So it's really kind of unlikely that the virus doesn't come back. So we need a vaccine, and here I would like to point out that the virus, as the previous speaker, virus neutralizing antibodies is the key to success and to long-term protection. So all we aim at is inducing neutralizing antibodies. And this we do, again, I repeat a little bit the previous speaker. So basically you have here the coronavirus, you see the spikes, this is down here, you see the spike again. And the most important domain in terms of vaccine development is probably the RBD domain, receptor binding domain, which binds to ACE2, the receptor. So if you have antibodies against RBD, they are most likely neutralizing. Now you can take RBD or the spike and make adjuvanted as the previous speaker does, or you can make an adenovirus vector as the Jenner and J&J does. You can make RNA, DNA, I wouldn't really do, or you can make RNA vaccines, and you can, and that's what we do, put it on virus-like particles. And this makes usually things very immunogenic. So this is our preferred way. We take the RBD domain and display it one way or another on an independent virus-like particle. I mean, the spike protein doesn't really make virus-like particle itself. So you need to find special ways to make virus-like particles display the RBD domain. And just to have a closer look at this, and then also we heard before, again, here is the RBD domain. You see here on the right-hand side, you see the ACE2 interaction with the RBD domain. And you see that the RBD domain has two glycosylation sites and one methylation, but that's probably not that important. But you know, all the reviewers make problems about the glycosylation. They say, oh, you know, your vaccine won't work because it's not glycosylated if you make it in bacteria, even though the previous speaker just said it works much better. And I agree with him, glycosylation usually rather hinders induction of neutralizing antibodies. But in any case, what we are also using is the receptor interaction domain, or the receptor binding motif. This is just in green here. This is the part of the RBD that really interacts with ACE2, and this is not glycosylated. So if we make a non-glycosylated version of this, that's actually the right thing to do because there is no glycosylation. Oops, nice one, came too quick. So here now what we are using is a virus-like particle based on cucumber mosaic virus. And this is highly immunogenic. I mean, as all virus-like particles really are. Additionally, we optimize it for the old elderly people, which seems to be optimal in this case here, because we introduced a universal T-cell epitope from tetanus toxin. Universal T-cell epitope means that pretty much every human will recognize it, and every human has been immunized against tetanus. So they will all have memory T helper cells against the toxin and consequently against our virus-like particle, which will enhance the IgG response of the people. It's highly productive, and now this is a number that we should really look at. So with a similar vaccine, we previously produced 1 kilogram of GMP material vaccine in a 200-liter bioreactor run. So if you do, or let's call it 1,000 bioreactor run, if you use a 1,000-liter bioreactor, you can make 10 to 20 million doses. And this is basically what makes our system unique. In addition, it's tested, it's using a tested and you know, widely used basis of vaccines, virus like products, but it is super productive. So you can really make tons of doses with limited effort. So that's why we actually think if our vaccine really works, we could supply large parts of the world. And our vaccine is not expected to cause enhanced disease, and this I explained in the next slide. But just that you don't forget, often people abbreviate Q-com mosaic virus as CMV, and then everybody thinks you use cytomegalovirus. So no, we use the Q-com mosaic virus. Just keep that in mind. So it's actually no human component to it. It's a plant, it's derived from a plant virus. So as we actually also heard before, the vaccine-induced enhanced disease can either be IgG mediated or Th2, or maybe Th17. I call it still Th2 here. And you see there are two ways IgG can enhance the disease. One is by enhancing infection. So if you have here this should be virus here, excuse me. If you have your virus binding to the IgG, it will be taken up by the Fc receptor, by the receptor for IgG, and then it enhances infection. But this only works for cells that actually can be infected. And you know, this is typically happening with dengue virus and macrophages. But the SARS viruses don't really infect classically macrophages. What can also happen is if you have the same mechanism here, but you take, it's again macrophage, you take it up by Fc receptor, it will be processed in the endosome and it will be better present on MHC class 2 molecules, and then you get more T cell priming. And this may be cause that cytokine storm people talk about. So that's an additional problem. And this may particularly be important for non-neutralizing antibodies because they only have a bad effect and they don't have the good effect of neutralizing antibodies. Then the other way to enhance disease, and this is certainly what's happening, for example, in RSV, and I still think in most of the preclinical SARS-1.
Hola, parece que hemos perdido a Martín. Oscar.
Sí, hola, disculpa Francisco, estoy revisando la señal de Martín.
Ok, quedamos a la espera, si no pasamos al siguiente ponente. ¿Tenemos señal o no?
Sí, nos parece que está todo correcto, pero no recibimos señal de Martín. Vamos a, si prefieren, pasamos al siguiente ponente para que no haya este delay y contactamos con Martín.
Okay. Let me introduce to Margarita del Vals. Margarita, are you here?
Yes, I'm here.
Yes, okay. Okay. Margarita del Vals.
But the only thing is I cannot share my, I guess I cannot share my.
Can you share your screen?
Can I? No, because the other one is being shared.
Estamos teniendo la sesión de Martín para que pueda compartir usted, doctora.
Yeah.
Okay. Thanks, Martin.
Yeah, I'm terribly sorry, my computer crashed.
Oh, yeah.
Oh.
Okay. Okay, so, Martin. Okay.
I'm back. And so the Th2 cells, they cause recruitment of eosinophils to the lung during infection. So after immunization, you get infected, this happens. And this really causes a lot of disease. Now I'm gone again.
You need to share your screen.
Ah, okay, to me it looked still like it was shared. But can you see now the slides?
Yeah, we see now.
Okay, sorry about that. Okay, so the eosinophils that correspond. So to my mind and to most people's mind, I mean, since Fc receptors are not involved in SARS-CoV-2 infected cells, so there is no way that's a problem. And if you actually are immunized, you expect to have low viral load. So there's a second mechanism here that enhances this, causes this cytokine storm only happens if you have a high viral load. So if you're immunized, if your vaccine actually works, that shouldn't be happening at all. So Th2 cells is certainly what you want to avoid. So in vaccine design, this is the most important part. So this is basically the same thing. So it is known from dengue that it's this cross-reactive low-affinity IgG antibodies that are not neutralizing the enhanced infection of macrophages. And again, SARS-CoV-2 is not expected to do this. Now the Th2 cells are a problem because, and I hate to say it, I mean, inactivated viruses and recombinant proteins formulated in alum, they have a reputation at least to do that. Now we just heard that's not the case, but in many examples in the literature it has been the case. So I think you want to add something that basically drives your response towards Th1 if you want to make a vaccine, and therefore TLR ligands, toll receptor ligands are a good thing to have. And so this is now our virus-like particle. We are using as a platform, and you can see EMMA is a beautiful thing. And what you can also see here, it actually loads, it's produced in this is also important to remember, it produces, it is produced in E. coli, not in plants. And it packages spontaneously RNA from E. coli. So you have a TLR7/8 ligand packaged, which is pretty much the optimal thing you can have. And you can see it's well defined by dynamic light scattering, mass spec, and so on and so on. And you see here in this little movie that we have inside the VP in red here, we have this universal T-cell epitope attached that should enhance immunity and immune responses in older people. So we did the first version of it where we just expressed RBD recombinantly and then chemically coupled it onto the virus-like particles. And you can see here that IS2 binds to these virus-like particles, and this is some more information you don't really want to know. But in effect, this demonstrates the vaccine contains coupled RBD domain. And now if you use this to immunize mice, you can see here you get a good response. Again, IgG response. It's an odd schedule to immunize mice. They were immunized on days 0, 7, and 14. And you have meanwhile realized that this was not a good thing to do, so you shouldn't boost so quickly. But we were a bit in a rush. But you see here in C, this is after 3 weeks here, after 2 boosts, you get a really high IgG response, and the cucumber itself doesn't really do anything, and also RBD alone doesn't really do a response. But I have to admit, this was done without an adjuvant, so maybe not the best chance. We didn't give RBD the best chance. And then we looked for competition. This is always a good thing to do. So your antibodies should compete between ACE binding to the receptor, to be ACE binding to RBD, and this is what you see here. So this is a competition analysis, and you see reduced binding of ACE to RBD. So the antibodies do what they're supposed to do. They block receptor interaction with the viral RBD domain. And then we did a neutralization assay. So again, this is the vaccine. So what we used as a readout is pseudotyped retroviruses. So the retrovirus, in fact, expresses the spike protein of SARS-2 rather than the one of the retrovirus, and now needs this to infect cells. And then we used, it had a luciferase gene in it to visualize infection. And also we used ACE2 transgenic cells rather than normal cells because we wanted to have the human ACE2, you know, being the receptor for the virus. And then you look at neutralizing titers. So you see the QMB, the line doesn't do anything, RBD alone doesn't do anything, but our vaccine actually induces good neutralizing titers. So this was a good start, but it was just not, you know, if you want to make a millions of doses in a year or a half a year, you cannot use a complicated system where you express RBD and then you couple it chemically to a virus-like particles. It's just a little too complicated. So we wanted to exchange the chemical coupling by genetic fusion. So we genetically fuse now the RBD domain or also the receptor binding motif into different virus-like particles. And again, this makes the virus-like part, the RBD domain here look like a virus, and you get a good response. And in addition, the VP contains RNA, as I mentioned, you make a Th1 response, and as I mentioned, it's optimized for the elderly, so it is kind of a good combination. And this is the same thing. So now we have two different strategies, or three different ones. The one here is what we've already done, is coupling RBD to the cucumber virus, and you see here it says CMV. So this is not cytokine virus, this is the cucumber mosaic virus. And then we have here the cucumber mosaic virus where we fuse now genetically the RBD or the RBM, so the receptor binding motif, into the surface of the virus-like particle. And we also have, as a second strategy, a different virus-like particle where we genetically fuse the RBD domain to the end of the C-terminus of the virus-like particle. You can see the difference already here down here for the genetic fusion in the middle. For the cucumber, you get beautiful virus-like particles, while you struggle to get something reasonable with AP205. So we seem to be solving this problem, but we have been focusing on the cucumber mosaic virus so far. And what we've been using is the RBM domain fused to the cucumber mosaic virus. VLP, this is basically the same system, but we made a mosaic particle, which means not every subunit has the fusion, because if you fuse it to all subunits, then it doesn't really assemble anymore, because the receptor binding motif disturbs the assembly of the virus-like particle. Now, GSK used the same strategy to make the RTSS malaria vaccine. They also made a mosaic virus-like particle. So this is not impossible. It's technically actually very easy to do such a thing. And if you look here by STS page, you see here, this is the subunit of the virus-like particle that is not modified. And you see here the subunit that is modified with the receptor binding domain, and you see it's about the same. So you have about half of the subunits are modified after expression as mosaic particles. Then you see here EM, so it's beautiful virus-like particles again, and you see here this dynamic light scattering. This is 3 measurements there, so they are quite homogeneous in their appearance, which is of course a good thing. And then we wanted to see whether ACE2 would bind to the vaccine, and it does. So you see here the binding so the cucumber mosaic virus doesn't really bind at all. Let's just some background. And here you see the receptor binding domain is an FC fusion molecule. It binds well to ACE2, but our vaccine actually binds at least as good as the RBD FC fusion molecule. So it binds the receptor. And then we tested a couple of monoclonals against RBD. They don't all bind because they don't all bind to the receptor binding motif, but this one does here, and you can see here you have as positive control this monoclonal binding RBD or spike. Does it better, but it's maybe not a big surprise. And here you see two different, this is the AP205 vaccine candidate, and this is our preferred candidate. They both bind the antibody as well. So they have the right epitope on the surface. And then we immunize mice with it, and this is, I just show you a few data. These are with 20 micrograms. This is all done without adjuvants. And you see here in black is the normal response. This is given on day 0, 7, and 14. Here it's given on 0 and 28, and here it's given on 0 and 14. You see 0 and 28 is, to my surprise, actually much better than day 0, 7, and 14. But you get a good response in any case. And here in red is you see if you treat the plates with urea. This usually gives you an indication of how well the antibodies bind. So it's an avidity measurement. And you can see they bind well. I mean, those don't, the 0.714 are the worst, but here you see not much of a difference. So you get high avidity binding to the, this is here the RBD domain. And you see the winner is if you give 100 microgram and immunize on D0 and 20 and 28, then you get a super response, which basically is not, is completely resistant to urea. So these are very high avidity antibodies. So they wanted to know the subclasses, and you all know 2A and 2B are most protective in the mouse, and the human would be IgG1. And IgG2A and B are indicative of a Th1 response, and again, this is what we want. And they are driven by TLR7, 8, or 9 engagement, and as you remember, the VLPs, they have TLR7, 8, and so they drive IgG2A responses. And here you basically just see a summary of all different regimens here and doses. But you see, you get a very good IgG2A response. You also get an IgG1 response, but you get a very good 2A, and you get a good T2B response. So this is what you wanted. So you get a response that is certainly good at a good IgG2A response. And then we wanted to look at IgA. I mean, IgA has the advantage of having a high avidity. So even if your antibodies may not be the best on the planet, they will still bind well because IgA is a dimeric antibody, meaning it has 2 IgA molecules linked together. So this is making it having a higher avidity. IgA is non-inflammatory, which might be also a thing you want in the lung, you know, that you don't have all these negative effects I was mentioning before by enhanced uptake by Fc receptor. It's important in mucosal protection, obviously, and it's also, again, like 2A driven by TLR7, 8, and 9 engagement. And so maybe expectedly, you also get a good IgA response here. This is here in green, you see 100 microgram again. Day 0, day 28 gives you, and this is a beautiful IgA response. And also if you give it a bit more often, earlier day 0, day 14, but again, day 0, day 28 clearly wins. But you get very good IgA responses again, as well against your protein. And now this is maybe the thing I was most surprised by now. What you see here in gray is just a response against RBD of our mouse sera. Obviously the best ones, day 0, day 28. And what you see down here is incredibly enough, these are all convalescent patients. And they do make neutralizing antibodies, by the way, but they are so much worse, it's untrue. So you get really extremely much better response in the mice against RBM than what you see in the humans that in fact have neutralizing antibodies. And now if you test for the affinity, before I said you use urea, which gives you a measure of the avidity. And here now you take, if you make a low coating density, if you give very little antigen on the plate in an ELISA, then the antibodies can only bind monovalently. And this kind of reflects the affinity. And you see again that the difference is even bigger. I mean, our mouse cells still bind beautifully, and those things here barely bind anymore. So our mouse cells have clearly higher affinity for RBM than what you see. What you see for the humans, cell. And then you can do the same thing for the spike protein. And again, our mouse sera, they clearly have the better titer than the human sera against the spike. The difference is less pronounced, but this is what you would expect because obviously the humans make antibodies against different spike epitopes, while we have only one spike epitope. Nevertheless, the mouse is much better. And if you do the same the low coating density assay to look for affinity, then in fact they become similar. So the mice are still better, but not in any way or shape as much better as it was for the RBD domain. But still, our mouse sera, they look better than the human sera.
Martin, sorry, we are a little bit late, so could you be finishing?
Yeah. Well, sure.
Sorry.
This is the same thing again for humans. You see that the mouse cell have the better affinity than the human cell. And here they also neutralize, is what you then would expect. And now I just would like to see what we plan to do we have two scenarios of the development. You know, it's a high COVID-19 scenario, so you still have the pandemic laws. Then we expect to start clinical studies in October, and we want to immunize the Swiss population in February. And then later on, we want to immunize a lot of people outside Switzerland. And in a low COVID scenario, when this pandemic laws fall, then we want to have. It's just going to be slow, because then you have really to do a phase 3 study before you get registration. So then the Swiss public immunization will be like Q3 2021. But this is still open, and we are currently talking to Swissmedic, which is the Swiss FDA, how they see the situation. And so this is all the people, where all the institutions working on it, and here's all the people working on it. Okay, that was it. Thank you.
Thank you, Martin. So you are planning start your clinical trials in humans in next fall, next October, I see.
Well, depending on the laws. Yeah. You know, this is just going to make a heck of a difference. You know, if they have to, this is, you know, it's not an RNA molecule. That thing's difficult to make. Yeah. So if you have to have proper GMP material, then this delays everything. So we expect, and this is pre-discussed with Swissmedic, that we can use a technical batch. Mm-hmm. But this is only the case if there is still the pandemic laws.
Your research supported by the government of Switzerland, or is it supported by any company?
It's mostly supported by my SNF grant, and also by a company called Cyber. Cyber is running everything. Yeah. And we just got now. I mean, we are signing a contract with our Ministry of Health. They're going to pay for everything. So yes, we will be supported by the Swiss government.
Okay. Any question from the panel? Okay, Martin, thanks for joining us today. Thanks.
Welcome.
To you. So let's go to the next speaker, Margarita Del Val. Margarita is a scientific researcher at the Severo Ochoa Center for Molecular Biology at the Spanish Scientific Research Council. She is directing the platform of this council, which has brought together 200 research groups focused on the pandemic. It's very interesting to hear from Margarita today. Oh, Margarita, you have the floor. Thanks for joining us today.
So thank you. Can you see my screen? Is that okay?
Yes.
Okay.
Perfect.
So then I'm going to present to you this platform that we have built together. It's a thematic platform focused on global health, but right now it's coronavirus pandemic, of course. It's a multidisciplinary platform because the Spanish National Research Council covers many topics, from human sciences to maths and over biomedicine, of course. And one special thing about it that is not very common in Spain is that it is mostly funded by private donations from major companies, but also from private donors. This is very common in other countries, like in the United States or in Great Britain, but this didn't used to be the case in Spain. So we also get some funding from the government, and that funding is mostly focused for the vaccine projects. But all these people are contributing to the type of projects that we are developing. We are not only involved in research, but we also want to start partnerships with the industry for development of vaccines. Of the vaccines we are currently in the research phase, and for the production of these vaccines, but also for antivirals. So right now we have 3 vaccine candidates, and there are some other 7 more prototypes in Spain. The National Spanish Research Council is it's one of the is the largest public research institute in Spain. It's the 5th in Europe, and as I told you, it covers all disciplines. It has 120 institutes across Spain in different places. It has some 3,500 scientists with a lot of graduate students, many technicians, and very few people contributing to the administrative support, which really could grow actually. So how is the platform? So the platform started when the pandemic started, and it all started from the National Research Council. They said, who wants to do some research on coronavirus? And so at the beginning it was over 150 research groups. Now we have some 250 or so. Not all of them are leading single projects. Many of them, many of the projects encompass maybe 3 or 4 different groups. And we don't have funding for all of them, so funding is competitive. And now we have over 60 research projects. We cover all aspects, from the last one, which Peter was mentioning, a good impact on communication of science, because we think that that is important now that there is a lot of demand on that. But we start with prevention of the disease. I apologize for the Spanish slides, but we still have not have time to translate them into English. Anyway, we start with prevention of the disease, and here, if we would have a vaccine, then we would be there. But this we include it here because we have the idea that this is global health and not only coronavirus, and we want to get to be ready for future pandemics or for future waves of this pandemic. So the second main topic that we're dealing with is how to get to know the virus. So there's a lot of basic research on the virus, genetics and the structure, and also to get to know the disease, how the severity correlates with the immune response and so on. Then we have a lot of research of immediate impact, like developing easier diagnostic tests, looking for how it is propagated, and containment and disinfection. We have a lot of people working on treatment, a lot of people working on antivirals, both with positioning of known drugs as antivirals and also on new antivirals developed on the knowledge of the virus itself. And we are also working on producing some therapeutic antibodies, not only plasma from convalescent patients. And we have another dimension to it, which is the impact of the pandemic on the social, political, and economical levels, as well as on the environment, which is also having so far a positive impact. And we also have people working on that, plus other people who are working on transversal studies, like looking for technology and applications for the cell phone and so on. So we have 3 vaccine candidates. This is the first one. This has been developed by the group of Vicente Larraga, this is his name here, at the Center for Investigaciones Biológicas, Margarita Salas. And he was working in a leishmania vaccine, and he immediately turned that platform into a coronavirus vaccine. This is a DNA vaccine, right? And this DNA vaccine is a plasmid that does not require adjuvants. It is a plasmid that doesn't have any antibiotic resistance, so that it is ready for human use. He's expressing the S gene of the coronavirus, and he's testing that expression in human cell lines. Will go to immunogenicity studies on normal mice, then to challenge studies to see whether it protects in transgenic mice, and then he will go into production. The good thing about this vaccine is that production at large scale was already done by the leishmania variant, the leishmania vaccine, so that he has already the factory growing, the factory prepared, and immediately he could start growing many doses of the vaccine as soon as they want to start. I mean, as soon as they have it ready, in parallel with making the animal experiments, so that they are ready also for the phase 1 and phase 2 human trials. The second vaccine has been produced in Center for National Biotechnology. The second and the third are produced in the same center by two completely different groups. This group is led by Mariano Esteban and Juan Garcia Arriaza, and they have been working in vaccines for a long time. They have been working for a long time in vaccines based on MVA, which is one of the vaccines that was used for eradicating smallpox from the world 40 years ago. So this vaccine was already used in many humans 40 years ago, and it is very safe. And it is even used right now for vaccination of researchers who work with vaccinia virus or who work with variola plasmids or anything like that. So the wild type MVA is licensed for human use already. So they have been working on vaccines based on MVAs for quite a long time, and they have been working with emerging diseases caused by viruses like chikungunya, where they managed to make a vaccine expressing many proteins of the chikungunya virus, and they got 100% protection in animals and in non-human primates. They also produced a vaccine with two proteins of the Ebola virus, and these two proteins were able to make a virus-like particle of Ebola, and they achieved 80% protection in mice, and with the Zika virus also they got a very good protection, expressing two proteins. So they use exactly this platform for going to the coronavirus, and what they're doing is that they are expressing the S gene in the MVA. They prepare recombinants in a two-phase protocol. Oh, this is not coming. Yeah, here it is. So they have a two-phase protocol for producing recombinants, and they have very stable recombinants based on MVA with some deletions, some insertions with relation to MVA, so that it is more immunogenic than MVA itself, and it still is as safe. And they will go for immunogenicity and efficacy preclinical trials, and also then for clinical trials. One good thing about this vaccine is that exactly the same platform was used before, not only for these three emerging viruses, but also for HIV. And in HIV, it went into phase 1 and phase 2 clinical trials as a therapeutic vaccine. So they know already how to grow the GMP quality vaccine, and they are also growing quite fast. And the third vaccine is the one that has been designed by the group of Luis Juanes and Isabel Sola in the same institute, in the Center for Biotechnology. And they are building on their many decade experience with coronaviruses. They have worked already with 6 of the coronaviruses, animal and human coronaviruses. And with the previous SARS, they produced an attenuated vaccine that was tested in animals, that was very, very efficient in protecting the animals, that did not enhance disease. And they noticed that that attenuated vaccine tended to revert to a more virulent vaccine. So with MERS, which came later, and everything is described in this paper, they developed a new type of vaccine where they deleted some segments of the virus, and they constructed a replicon that now it is replication competent, so it can replicate for production of the vaccine, but it is propagation defective, so that as soon as you use it as a vaccine in a mouse or in a human subject, it will express all proteins, most of the proteins of the virus, but it will not be able to propagate. So this is an additional safety issue that they have introduced into the vaccine. So it is attenuated and it is propagation defective. So both things, so that it does not revert ever to a wild type virus. It is completely attenuated and it provides full protection against challenge. So they are the MERS and the SARS. So they are working into that. This is a more complex vaccine, and the way they are envisaging how to go on with it is that they plan to have these RNA replicons and to mix them with nanopolymers to produce a nanoparticle, and to use this as the vehicle for the replicants that will be used for in vivo delivery of the vaccine. And as Africa was saying, they chose to use the intranasal delivery route because this mimics exactly the way the coronavirus infection takes place by the intranasal route. So they expect to induce a very broad immunity to many antigens and very similar to the natural one. So they expect to have a very good immunity to the virus. They have a second version, which is by providing additional proteins, which is under intellectual property, and making virus-like particles of this type. These are not from this virus right now, that look very similar to the original virus. So, and finally, this is my last slide. So yes, I wanted to discuss some of the three vaccines in parallel. So the DNA one based, it is only one antigen, which is maybe a limitation as is the NDA so far, as compared with the attenuated replicon-based vaccine, which is more complex in the types of antigens that it has. Because it is more complex, it is expected that it will induce a more balanced immunity, as I mentioned, but also because it is more complex, it will be more difficult and slower to produce, maybe. Because the technology is quite different to what has been used previously for vaccines, it may face different problems. Of course, one of the problems with DNA vaccines is potency, but maybe we don't need a vaccine that is 100% efficient or 100% potent. Maybe we can get a 60% efficiency of protection. Maybe that could also lead to very strong immunity for the population. With MVA, one of the questions that we know of, which of course is not posed by other of the vaccines, is the duration of immunity. We know it with MVA wild type, when it is used for human use for researchers working with vaccinia or with, as I said, viola DNA segments. We know that memory does not last for many years, but maybe 2, 4, 6 years. It is declining with time. So maybe this could be improved with a boost with a different vector. But so far the design is only MVA expressing the COVID-19 proteins. And one problem is that the elderly may have immunity against the vector because people over 50 in Spain or 55 were vaccinated with the smallpox vaccine. So that could be a problem. However, the MVA, so it could be a problem, but not a full problem, because the thing is that people that are vaccinated with MVA can, with the smallpox vaccine, this MVA wild type still works. So it might be weaker or not as strong, but it does work and it induces antibodies. So this is fine. One of the limitations of the full coronavirus vaccine is that it may or may not suffer from the cross-reactivity that was described first by Rafael and then by Africa, that was published recently by the Sete and Kramer group, but not by other groups. The cross-reactivity of the T cells mostly that occurs among coronaviruses. It is a low potency, low activity cross-reactivity, but it may to some extent contribute to lower the efficacy of the vaccine. These are the limitations. What are the advantages? The advantages, as I said, that for the DNA, that large-scale GMP production is already there, so it will immediately be produced and it is safe as well. For MVA, the production will also be very fast because they have very good experience with the GMP production as well, but they don't have the factory ready for it because that was produced elsewhere and now that is no longer available. The one that was used for HIV, for phase 1 and phase 2, sorry. And then the point that I mentioned, that it is licensed for humans, it induces good B and T cell immunity, so it is broad even when it's only one antigen. It is also very safe and has a very good safety profile. The whole virus, the whole attenuated virus, this one is complex, and therefore we expect it to induce all arms of the immunity. It is good because it is the formulation is meant for intranasal inoculation, and it is expected also to be safe because it has two safety issues inserted into it. One, the attenuation, and second, the propagation deficiency. And then these again are the people who are producing them. So these are our three children of the National Spanish Research Council, and they are all different. We love them all, and we are going to foster them all. Thank you.
Thank you, Margarita. Excellent presentation. Congratulations. So, do you have any schedule to start the human clinical trials?
Not really. I mean, it depends on. I mean, we are quite. We have to. We want to go on the safe side. We don't want to be that fast. We know we are not going to be the first vaccine in the world, not even the second. But we want to do all the animal experiments, and we want to start setting everything for the clinical assays as well at the same time. And before that, of course, for the production of the batches for the clinical assays. Maybe end of the year with some of them if everything goes perfectly, but one has to expect that maybe not everything goes perfectly. It's difficult to foresee actually, you know? But people are working very fast, and we are working. The whole platform. The good thing is that the whole platform is working on all the things that they are not doing. So they are focusing on research, and we have many people who are helping them, which is not usually in Spain at all, and people who are helping them with all the other issues, like this clinical trials and the production and the partnership with industry and so on. So that's it.
Excellent. So, Margarita, thanks for joining us today. Your presentation was very helpful. Thank you. Thank you. Let me introduce the next speaker. It's Maria Luisa Avila. She's the head of pediatric infectious diseases of the infectology service at the National Children's Hospital in San Jose in Costa Rica. She was the Minister of Health for 5 years in her country, Costa Rica. I know her opinion is very important for many researchers and policymakers in Latin America. So, pura vida, Maria Luisa. Thanks for joining. Thanks for being here today. So,
hola, Francisco. Muchísimas gracias por la invitación. ¿Me escuchan bien? Disculpen.
Perfecto.
Excelente. Bueno, primero agradecerle a Francisco, al Instituto Balmis, por la oportunidad de compartir con tan excelentes ponentes y con las personas que se nos unieron vía internet. Yo voy a hablar en español, mis diapositivas están en inglés. Como pueden ver, yo voy a hablar un poco de las perspectivas en Latinoamérica relacionadas con el COVID-19 y su prevención con relación a vacunas. Para esta conferencia no tengo ningún conflicto de interés por declarar, y mi agenda va a ser una visión muy rápida de lo que ha sido el COVID en Latinoamérica, las vacunas que ya han sido previamente tratadas, nuestras perspectivas regionales y algunas conclusiones. Latinoamérica es una región terriblemente heterogénea, como ustedes pueden observar. Por supuesto que si incluimos Canadá y Estados Unidos como parte del continente americano y nos referimos a ellos dentro de esta presentación, podemos ver en esta diapositiva que fue del Índice de Seguridad Global que salió el año pasado, pero que este año fue adaptado para la lucha contra el COVID, que la mayoría de los países de Latinoamérica no estábamos preparados para hacerle frente al COVID-19. Hay algunas excepciones, como pueden notar en el mapa, donde mi país era uno de los que se consideraba que podía hacerle frente con éxito a una eventual epidemia o a una pandemia, y paradójicamente, aunque Estados Unidos aparece como un país que estaba muy bien preparado, lamentablemente no fue así. Como ustedes saben, hay más de 100,000 muertes en lo que va de la pandemia, y se prevé que a raíz de los conflictos sociales que en este momento el país tiene, podrían aumentar. Así es que ningún país necesariamente rico de ingresos medios o país considerado pobre podría predecir cómo iba a ser su comportamiento con relación a la pandemia. Obviamente los países africanos, ya todos nosotros sabemos que tienen algunas particularidades que van a hacer que la respuesta a cualquier emergencia sanitaria pues no sea necesariamente la que todos nosotros desearíamos que ocurriera. En mi continente, en Latinoamérica, los países que más casos han presentado han sido Brasil. Es posible que después de Estados Unidos, Brasil sea uno de los países que presente un número importante de casos, como ya lo está haciendo, y también es el que en este momento ha reportado la mayor cantidad de muertes. Le sigue Perú, México, Chile, Colombia y Argentina. A nivel de Centroamérica, una de nuestras principales preocupaciones es Nicaragua, porque hay una negación gubernamental de que hay una emergencia sanitaria y por ende las cifras no podríamos validarlas, no son cifras que puedan ser creíbles por más oficiales que se presenten y por supuesto en un contexto de interrelacionalidad del continente, pues es motivo de preocupación. Aquí surge un concepto muy interesante que es el de sindemia, donde una emergencia sanitaria se va a ver influenciada por aspectos sociales, políticos y por supuesto económicos. Y posiblemente en el continente de las Américas sea donde más se esté viendo este fenómeno de sindemia. Y posiblemente lo que lleva a pensar que América Latina va a ser, después de Europa, el epicentro de mayor cantidad de casos. Como mencionaba anteriormente, no estamos del todo preparados para el virus como región y esto podría ser que eventualmente tengamos mayor cantidad de casos de lo que ha ocurrido en Europa. Al momento de esta conferencia, con datos actualizados el día de ayer, ya el continente llevaba, América Latina, aquí no estamos incluyendo Estados Unidos ni Canadá, América Latina ya había confirmado 3 millones de casos y estaba superando las 50,000 muertes en 33 países que lo reportan. Y un aspecto fundamental a tomar en consideración para nuestra región es la economía informal, la cual se calcula en un 55%. Lamentablemente nuestra región es una región con mucha inequidad social y económica, con gobiernos muy diferentes, con tendencias políticas muy diferentes, que hacen que en vez de estar unificados, tengamos diferencias muy marcadas en cuanto a la respuesta que podemos dar a una pandemia como la que estamos afrontando el COVID-19. El estado de las vacunas ya previamente ha sido mencionado, sin embargo, quería dejarles esta diapositiva por lo siguiente. La manera tan acelerada como se ha venido manejando la pandemia, por la necesidad obvia que esto representa, ha hecho que muchas veces nosotros acostumbrados a procesos científicos más lentos, nos veamos abrumados con una gran cantidad de información que no necesariamente ha sido validada por pares. Recientemente, el día de ayer, se retira un artículo de Lancet relacionado con la hidroxicloroquina que demuestra que a veces ir tan rápido no es necesariamente lo mejor. Y con vacunas, quizás una de las preocupaciones es que todas estas fases que tradicionalmente se han respetado para que llegue una vacuna segura y efectiva a la población, se estén corriendo demasiado rápido, incluso hablándose de algunas aprobaciones por asuntos de emergencia, lo cual nos hace pensar que tenemos que estar muy cautos a la hora de analizar los datos para podernos asegurar que lo que le vamos a ofrecer a la gente sean vacunas seguras, efectivas y lo suficientemente analizadas para que no representen un riesgo para la población. ¿Qué es lo que necesitamos para obtener una vacuna? Bueno, ya previamente se habló de la importancia de conocer la inmunidad post-COVID-19. El desarrollo de vacunas candidatas también ha sido ampliamente discutido y nosotros esperamos pues que de estas vacunas candidatas salgan varias, no solamente una o dos, que podamos eventualmente utilizar. Los necesarios estudios preclínicos en animales de experimentación y por supuesto los test en las pruebas en humanos voluntarios, pero siguiendo aspectos regulatorios que ya nos han demostrado que son absolutamente necesarios. Para esta pandemia necesitamos una manufactura de gran escala. No sabemos necesariamente si esto va a pasar o no va a pasar, y posteriormente una distribución de esta vacuna. Una distribución que no va a ser fácil. No sabemos si el país productor, lo más probable es que esto pase, quiera dejarse la vacuna solamente para su población, o bien si hay posibilidades de hacer una distribución hacia cuáles países es que se va a enviar parte de la producción de vacunas. Y por supuesto, esto para nosotros en Latinoamérica es motivo de preocupación. Hay muchas vacunas candidatas de todos los diferentes tipos que también de previo los que antecedieron en el uso de la palabra lo comentaron, y actualmente hay al menos 8 vacunas candidatas que están en evaluación clínica. Sin embargo, son evaluaciones clínicas muy preliminares. Hay 2 a las que les tenemos enorme esperanza: la de Moderna, que también ya fue discutida, del National Institute of Health de Estados Unidos, y la vacuna de Oxford, donde ya en Inglaterra se están corriendo algunos ensayos clínicos. Se cree que para julio, según informó la Organización Mundial de la Salud, se van a seleccionar 14 vacunas candidatas. Importante mencionar que desde el punto de vista que anteriormente les comentaba de la sindemia, es posible que algunas vacunas en Estados Unidos sean aprobadas con un mecanismo de emergencia por lo que ahí está ocurriendo, y la vacuna de Oxford, pues que se está en este momento probando, podría eventualmente ser una buena esperanza para nuestra región. Esto también ya ha sido comentado. Estos son los diferentes fases y las diferentes vacunas que fueron publicados ahora en Nature Review, donde podemos al menos pensar que tenemos esperanza de que haya más vacunas que podamos estar utilizando en los siguientes 12, 18 o 24 meses. Como ustedes muy bien saben, pues hay un árbol de puntos que hay que tomar en consideración a la hora de decidir si se introduce o no una vacuna. Evidentemente, la identificación del problema lo tenemos claro. También tenemos claro quiénes son la población de riesgo con relación al COVID. Es viable esa intervención, y por supuesto los estudios costo-beneficio, costo de la enfermedad tienen también que ser definidos, dando con esto lugar a una eventual oportunidad de transformar lo que el COVID-19 nos está ocasionando. Por otro lado, no hay duda que esto es un problema de salud pública. Incluso yo diría que es un problema que trasciende a la salud pública y que por ende requiere una respuesta social. Ya Peter Hotez nos habló del problema de los antivacunas y los anticiencia, y aquí vamos a necesitar una negociación y un apoyo político fundamental de los gobiernos latinoamericanos para poder contar con las vacunas. Creo que una de las importantes conclusiones a las que nos puede hacer llegar esta pandemia es que la vacunación tiene un enorme valor social, y quizás esa pueda ser una de las fortalezas cuando posicionemos la necesidad de contar con vacunas seguras, efectivas, pero sobre todo vacunas que estén al alcance de quienes la necesitan y no necesariamente de solo quienes puedan pagarla. Y relacionado con esto, mi gobierno, el gobierno de Costa Rica, ha estado trabajando con la Organización Mundial de la Salud, instando a la mayor parte de los gobiernos a que puedan unirse y abrir la investigación y la ciencia del COVID-19 a beneficio de la humanidad. Este es un tema que nos afecta a la humanidad, y por ende la solución tiene que ser para toda la humanidad, y lo que se pretende es que tratamientos, que vacunas no necesariamente tengan patentes, que puedan ser producidas en una escala mayor a lo que normalmente estamos acostumbrados, y por ende estas puedan llegarle a una cantidad importante de la población. Oportunidades las tenemos. Creo que es hora de que la visión en salud a largo plazo, que trascienda gobiernos y que trascienda países, sea una realidad. Si en algo podemos unirnos es en vacunas. Si las enfermedades no tienen frontera, las vacunas tampoco deberían de tenerla. Políticas universales son absolutamente necesarias. Estas políticas tienen que priorizar los aspectos sociales, tienen que tener recursos que nos permitan hacer intervenciones basadas en la evidencia. Sin lugar a dudas, una vez que se tengan vacunas, el análisis, el monitoreo y la evaluación de los esquemas van a ser basados en las realidades epidemiológicas que cada país tenga. Y una frase que para todos los que en algún momento hemos trabajado en salud pública es: la salud basada en los una vacuna, hay una serie de problemas relacionados con el ámbito de salud en los países, en la manera en que prestan sus servicios y que atienden a las personas enfermas, y una visión más amplia de que la salud no solamente es la ausencia de enfermedad, es lo que vamos a requerir, y eso se logra interviniendo en las causas de las causas. Ya para ir concluyendo, en la última década hemos tenido avances importantísimos en vacunación y se han prevenido millones de muertes. Esperemos que uno de los legados que nos deje esta pandemia no sea muchas muertes más por sarampión, muchos más niños paralizados por polio, porque a raíz de la pandemia no tuvieron la oportunidad de accesar a un servicio de salud y ser adecuadamente vacunados. Sabemos que la introducción de vacunas contra neumococo, rotavirus, contra meningococo, en esquemas universales ha prevenido muchísimos miles de muertes cada año en la población pediátrica, y que el beneficio de la vacuna sigue siendo la prevención de la enfermedad, sobre todo para aquellas personas más vulnerables. Esta pandemia nos ha traído a todos muchísima incertidumbre, individual, como colectivo, como país, como sociedades, y parte de esa incertidumbre es: ¿tendremos o no tendremos vacunas para todos los que las necesitan? ¿Vamos o no a contar con medicamentos realmente comprobados? Y acá me uno a las palabras anteriores de Peter con la importancia de no caer en la anticiencia y que podamos efectivamente combatirla, porque esto ha sido uno de los problemas que más incertidumbre nos ha venido ocasionando. Mahamud Ar-Rahman acaba de decir algo que es absolutamente cierto y que creo que todos compartimos. La salud no es solo un derecho humano, es un prerequisito para el desarrollo, y la salud debe ser para todos. Sin embargo, entre las perspectivas que tenemos como una región no necesariamente de las más ricas del mundo, las vacunas posiblemente van a ser para pocos afortunados y felices ciudadanos, y la salud no necesariamente va a ser para todos. Sin embargo, pues vamos a esperar poder trabajar para que las vacunas lleguen a todos los que la necesitan. Agradeciéndoles su atención, les dejo mis contactos y por supuesto preguntas son muy bienvenidas. Muchísimas gracias, Francisco y amigos.
Muchas gracias, María Luisa. Encantado de oír tu conferencia. Tenemos varias preguntas de nuestros amigos de Latinoamérica. Hay una, si cree que puede ser posible la aprobación de vacunas sin las suficientes garantías por presiones socioeconómicas.
Sí, precisamente eso es una de mis preocupaciones, que puedan aprobarse vacunas que no hayan pasado todos los filtros de seguridad, y sobre todo que el tema se ha politizado mucho. Creo que aunque somos un foro científico, la política nos ha influido no siempre positivamente. Vemos lo que ha pasado en Estados Unidos, en Brasil con el presidente Bolsonaro, Centroamérica, Bukele en El Salvador, los Ortega en Nicaragua, pues obviamente hace que hayan una serie de presiones políticas que para bien o para mal van a influir en el tema de la vacunación. Es posible que Donald Trump decida nacionalizar su vacuna, o ya ha ofrecido comprar vacunas a altos precios a otros productores, así es que son parte de la equidad en salud que tenemos que discutir y conocer.
Otra pregunta, ¿cree que el costo de las vacunas sea un reto para obtenerla en países latinoamericanos?
Sin lugar a dudas, posiblemente las primeras vacunas sean sumamente costosas. Habrá que invertir en ellas y buscar mecanismos eficientes para poderle hacer frente a la demanda.
Okay. Y por último, ¿Tiene usted alguna información de cómo se ha comportado la epidemia en los sanitarios en Latinoamérica?
Sí, no mucha porque se ha publicado poco. Sin embargo, ha pasado muy similar a lo de otros países donde las personas que han estado en la primera línea de combate, que están sumamente expuestos a muchos pacientes COVID positivo, han sido los que más han enfermado. Muchos han sido lamentablemente porque no tienen todo el equipo de protección personal y otros también muy lamentable porque no lo usan de manera correcta. Entonces son parte de los temas en los que hay que enfatizar en los próximos días.
Muy bien, María Luisa, muchas gracias. Si acaso al final tendremos alguna pregunta más. Muchas
Claro
gracias.
que sí, aquí me quedo. Hasta luego.
Well, we go ahead with the last speaker, which is Javier Díaz Domingo. Javier is head of the vaccine research area and is the scientific director of public health, both at the Foundation for the Promotion of Health and Biomedical Research in Valencia. He's a pediatrician and has spent more than 20 years doing clinical epidemiological research on vaccines and immunopreventable diseases. He's been a principal investigator on more than 20 vaccine clinical trials, and he's an expert advisor to the European Medicines Agency in the area of pediatric medicine. Thank you, my friend. Thank you for being here. You have the floor.
Thank you very much indeed, Paco, for joining, and thank you for. I've been looking at who is joined, and I got very good friends from Costa Rica, Lithuania, Panama, Greece joining. So, hello everybody, and sorry because we are a little bit late. And I would like, as a last, let me see whether this is this one. Yeah, this is the last presentation. I would like to go through how the vaccine is going to be used in Europe, because we may have very good vaccine or not, but definitely it is very, very important to be vaccinated. And as we have heard in the United States, and it's not in Texas, it's in the whole United States, in a poll, about half of the population will not vaccinate with the new COVID vaccine. About 40% are unsure, and 20% would definitely say that no. And those that will not vaccinate or are unsure is because of the safety issues. And there's a lot of people who still think that a vaccine can produce the disease, and they are quite scared of that. If we see how nowadays the information is transmitted, and it's mainly through social networks, and this is something is been relatively published last month, and we can see how the anti-vaccination movement in this is in Facebook, and we can see in green is people who are talking about vaccines, but they are not clear whether they will vaccinate or not. Those in blue are really those pro-vaccines, and those in red are anti-vaccine. And we can see how the anti-vaccine is growing, is much larger now than the pro-vaccine. And this is talking about vaccine in general. But very important is how those pro-vaccines are separated away from the vast majority of people who are thinking, who do not take a position, while the anti-vaccines are right in the center of them. So that means that the anti-vaccine lobby is in a very good position to spread bad news towards vaccination. And that includes definitely the COVID vaccine. So when a person decides to vaccinate or not to vaccinate, it's not that individual decision, but it has a lot of determinants around that. The last decision is individual, and that's because of the knowledge, attitudes, and skills. But there are many others who are interpersonal. It's what the family, what the friends think about that. What the organizational is, how the system is organized, and that includes the GPs. the community and the public policy. So we should, when thinking about the COVID vaccine and how we are going to implement that, we need to think that we should aim to all these areas if we want to have a good vaccine coverage. So, because where do really people look for information and who do they trust? So definitely the first area of information is in Google and then social networks. Then is the relationships, the family and so on. And the last one is their GP or the pediatrician, where they really trust. And we have shown in different studies that people who is not completely for the vaccine, if his pediatrician or their nurse is an advocate for vaccination, they end up being vaccinated. The problem is, where do healthcare providers get the information about the vaccine? And unfortunately, I must say that most of the healthcare providers do not get that from PubMed. Initially, there's a lot of doctors who go to Google, and mainly it's not Google Scholar. They use a lot of the social network. There's a lot of people who trust the people who they follow on the internet. Definitely, with this type of meetings, we are doing something, and very few are trust or are looking at the scientific literature. So that means that we, with actions like the one that we are doing now, and with other actions, we should aim at those places where the healthcare providers get the information. But we have to learn from the past, and we can think the last pandemic that it was much or was less severe than we expected, and definitely less than the COVID, which is the H1N1 pandemic in 2009. Everybody was wishing to have a very good vaccine at the early beginning when we had the news that the pandemic was coming and so on. However, the time between that the pandemic starting and when we had the vaccine, then it appeared the perception of the WHO decreased because they say they were sold to the industry. They saw the vaccines as an industry benefit. Some safety concerns were rose, and therefore there was a mistrust of the vaccine, and then the vaccine coverage was not as good as expected. Before that, and as the pandemic was not expected, what we had is that we had done some studies on candidate vaccines of influenza. In fact, the study group in Valencia starting the clinical trials of those vaccines in children in 2005. So that means that 5 years before the pandemic, we knew a lot of about the vaccine, and we knew much more about the influenza virus that we know about the corona. So we were not prepared for, although we expected the pandemic, we were not prepared. So different groups all over the world prepare some studies before the pandemic or during the pandemic, and they try to get the basal prevalence of different potential adverse events of the new vaccine, as the convulsions, the GBS, Bell's palsy, autoimmune diseases, vasculitis, myelitis, even sudden death. So we were relatively prepared to assess the safety of the vaccine on these pathologies. But unexpectedly, we had a pathology, which is narcolepsy. And it appears, and it was a big buzz with the vaccine. And as we were not prepared globally to assess the risk of the vaccines, then we had the problem with the same vaccine produced in Europe had a high relationship with narcolepsy, and we will try to explain later what happened. However, the same vaccine produced in Canada and had slightly different purification mechanism. There was no association at all with this narcolepsy. So, do this vaccine produce narcolepsy or is associated with narcolepsy or not? It is unclear. What it is, it's been shown is that when the first idea of the association of narcolepsy and this adjuvanted vaccine that came from the Nordic countries of Europe appeared, so there was a few cases associated temporarily, but then it came to the press. It's here awareness, and it not only came to the press, but there was also an economic compensation to those subjects who had narcolepsy due to vaccination. And that meant that many cases, once we had the awareness, there was a lot of cases that maybe they had started previously or late after vaccination with that excess sleepiness, but they were all associated to the vaccine. So it was that a real association of narcolepsy with these adjuvanted vaccines, or was not? We work in a study which was called SOMNIA. It was a global epidemiological study that was funded by the US CDC, and we studied together with colleagues from Taiwan, from other areas of Europe, Argentina, and Canada, and we couldn't find any association of the vaccine with narcolepsy. So what we learned is that it is important to have ahead of having a vaccine, everything prepared to assess the benefit risk. And as been mentioned today, these new vaccines are having these accelerated procedures for vaccines. That means that all the studies are going to be shortened, and that definitely when we have these vaccines on the market, we will not know as much as we would like about safety and effectiveness. And then the need for an active pharmacovigilance is very, very important. And that is what the European Medicine Agency has done, and they have organized, they are trying to organize a network in which we are included, in FISABIO we are included. That network to assess the benefit risk of the new vaccines in Europe when they come will be already set up. The leader is the University of Utrecht and back for EU. And as I mentioned, FISABIO, which is my institution, will be in charge of organizing a network of hospitals to assess the effectiveness of the vaccine. But these vaccines, and this has been mentioned, are going to be very challenging. And we are worried because it's been already mentioned, the enhanced disease by vaccination. And although some vaccines are trying to prove that they will not produce, the European Medicine Agency really worried with the potential enhanced disease by vaccination. And that enhanced disease, we learned about that with the RSV vaccine that was produced or was studied in the 70s. And that vaccine, the children that were vaccinated with that vaccine had a more severe bronchiolitis, and it's been explained why. But this is something that is worrying. The second challenge is that if you see most of the more advanced vaccines are developed in new platforms, and a platform is how the vaccine is developed. So there's no RNA vaccine already in the market. There's no DNA vaccine. There's not a vaccine based on non-replicated vectors. So we do not know how they are going to be performed once they are in the market. So the European Medicine Agency and other European agencies are also worried with these new platforms and the safety of the vaccines produced on that. So that is why we should be very cautious on the post-authorization studies. I think this is all. The conclusion is that the COVID-19 might be a turning point for vaccinations. If the vaccine works, people will be happy with new vaccines and with the vaccines, but if we fail with the vaccine, if we had a vaccine that is not well understood by the population or is not accepted, then maybe it will be bad for all the vaccination programs. And of course, these large pre and post-marketing studies are needed to maintain or improve the vaccine confidence in all over the world. And this is, thank you very much.
Thank you, Javier. Excellent. We have time for more questions. I asked the panels to turn on the video if you want. We can share the final question, final remarks. So I'm going to speak Spanish for a little. Hay una pregunta repetitiva de todo el mundo que supongo que la habéis tenido que contestar mucho en los últimos días. Y es en una visión optimista, ¿cuándo calculáis que puede haber una vacuna disponible para ser utilizada en la población general? Voy a preguntar uno por uno. Primero empieza Javier.
Bueno, es la pregunta del millón, la de la bola de cristal. Fíjate, si realmente los procesos de fabricación de la vacuna fueran los habituales, tardaríamos varios años. De todas formas, las agencias de medicamentos están acortando los periodos e incluso se dice de no hacer fase 3. Con esta visión, pues a lo largo del año 21 puede que tengamos alguna vacuna de nuevas plataformas, porque tendrán que ser vacunas ARN desde producción muy fácil, porque hacer una vacuna de las que tenemos ahora, que llevan meses de producción, pues tardaría, aunque esté autorizada, que una vez está autorizada la vacuna, luego hay que producirla. Luego tendremos que tener buenas vacunas y fáciles de producir. Con lo cual yo calculo que desde luego no antes del verano del 21.
Okay. África.
Sí, estoy de acuerdo. Y además también con lo que comentaba María Luisa, hay que ser muy cauto con el tema de la seguridad. Y realmente no saltarse pasos ni por presiones políticas ni por temas económicos. Creo que también está la reputación de si esas vacunas que se pongan de forma rápida luego fallan o tienen efectos secundarios. Yo creo que aquí hay que ser muy responsable y no dar saltos al vacío.
Rafael.
Bueno, yo no tengo experiencia directa, yo no trabajo directamente en vacunas, ¿no? Pero yo diría que probar la eficacia es ahora el reto principal, ¿no? Probar que la vacuna tiene realmente eficacia para proteger de la infección o por lo menos proteger de la enfermedad grave. Eso es algo que todavía no sabemos que se puede lograr y ese es el reto principal.
Javier, alguien está preguntando qué mecanismos tiene la EMEA, la Agencia Europea del Medicamento, para vigilar esos posibles efectos secundarios de las vacunas.
Bueno, pues estamos montando un mecanismo complejo. El mecanismo de seguridad va a ser fundamentalmente con real world data. Dentro del proyecto en el que estamos involucrados, se está montando una red de centros europeos que son capaces de tener datos en vida real, básicamente es en bases de datos, y estamos organizándonos todos los que tenemos este recurso para de una forma muy ágil ser capaces de analizar la seguridad de la vacuna en tiempo récord. Entonces, eso es lo que estamos trabajando ahora antes de que salga la vacuna.
Alguien está preguntando si es posible acortar la obtención de vacunas solapando las fases.
Sí, básicamente eso es lo que está proponiendo las agencias de medicamentos. Si queréis ver cómo se va a hacer, en la página de la EMA, de la Agencia Europea del Medicamento, hay todo un documento que explica cómo acortar los periodos. Y acortar los periodos es tanto acortar los estudios como hacer menos estudios y luego también disminuir los tiempos de trámite con la idea de sacar las vacunas lo antes posible.
Okay, no sé si está Margarita del Val.
Sí, lo que pasa es que no nos dejan entrar. No sé por qué. ¿Se podría arreglar eso?
Sí, te oímos perfectamente, Margarita. Ahora,
Vale, ahora ya sí. Es que no me daba acceso. Yo no lo he mencionado, pero desde luego yo estoy preocupada por el problema de la velocidad y yo insisto en que no podemos comprometer la seguridad de las vacunas bajo ningún concepto. Podemos invertir en varias fábricas a la vez, como dice Bill Gates, y porque eso gana a lo mejor velocidad quien tenga dinero para hacerlo. Podemos acelerar ir produciéndola y a lo mejor tener que tirarla, pero jamás podemos acelerar en comprometer la seguridad. Yo creo que eso nos va a hacer que la vacuna nos dé una bofetada de vuelta. Lo has dicho tú también, Javier. Habéis comentado datos de Estados Unidos, pero en Francia también salió el otro día en The Lancet. Han preguntado, ¿usted se pondría la vacuna de la COVID-19? Y el 26% dijeron que no. Es lo mismo que decían antes. Uno decía, bueno, a lo mejor es porque no ven que existe el sarampión y por eso no se quieren vacunar. Desde luego no, esto lo están viendo y tampoco se quieren vacunar de esto. Hay una desconfianza que no podemos crearla con estas vacunas. Tenemos que ir con mucha cautela. Yo estoy de acuerdo.
De hecho, si me dejas participar, Paco, con la vacuna la vacuna pandémica de la gripe, que fue una vacuna muy buena, y eso creó ya un efecto de desconfianza hacia las vacunas. Es cuando se empezó a decir que si era para beneficio de la industria, que los estudios no estaban bien hechos, y generó desconfianza. Y parte de lo que estamos viviendo ahora de las epidemias tienen su origen en la pandemia del 2009. Con lo cual, y fíjate que llevamos ya años trabajando con esa vacuna. Luego esta que va a ser un año un poquito más, va a ser para tomarla con cautela.
Margarita, has presentado las 3 vacunas que hay en desarrollo más avanzadas. Te voy a poner una pregunta, un compromiso. Son como las 3 hijas del CSIC. Tú como una de las madres del CSIC, sé que es muy difícil elegir entre las hijas, pero ¿cuál dirías que es la más lista de las 3?
Yo creo que la más completa, que es la atenuada y basada en replicones, es la más completa. Es la que más va a tardar desde luego en llegar y lo reconocen también los investigadores. Pero bueno, están trabajando en ella como si esto no fuese una emergencia porque piensan que aunque se llegue tarde es importante tener una buena vacuna. Pero la predicción la verdad es que es difícil porque hay veces que uno se hace una idea con una vacuna y se cae por algo. O se puede caer por la producción, pero se puede caer por alguna reacción adversa que uno no espera en absoluto. Pues la verdad es que es difícil y por eso, porque es difícil y porque las 3 son tan distintas en todo, en cuanto a producción, en cuanto a facilidad, en cuanto a velocidad, estamos pudiendo apostar por las 3 a la vez. A lo mejor en algún momento no se puede, pero ahora estamos por las 3.
Interesante, ¿no? Además, sería una vacuna intranasal, que es muy, muy interesante para la hora de aplicar.
Pero quizás no sé lo que opináis los demás, que sabéis de inmunidad también. Yo no sé si con las enfermedades respiratorias, que tenemos una inmunidad que permite reinfecciones a lo largo del tiempo, Yo no sé si la inmunización intranasal va a ser la solución, no sé si queremos tener una inmunidad que dura poco igual que la natural o querríamos tener otra mejor. Es bueno tener una inmunidad como la natural usando la vía natural de entrada, que es lo que yo diría, pero esta no es la mejor inmunidad posible. ¿Deberíamos buscar otra ruta?
Sí, interesante.
Si me permites, yo creo que hay un tema también que es la producción de IgA, ¿no, Margarita? El que se pueda tener una protección en la zona de entrada con la inmunoglobulina A, la consigues mejor por vía mucosa que por inmunización sistémica. Esa podría ser una ventaja. Yo tengo alguna experiencia con inmunización intranasal y desde luego la respuesta sistémica es mucho menor que si haces una inmunización subcutánea o intramuscular. Pero en este caso, al ser una infección respiratoria, pues a lo mejor se consigue realmente una vacuna muy eficaz por vía intranasal. A mí la IgA me parece que es algo que hay que mirar en la respuesta a estas vacunas porque necesitamos tener esa protección en el ámbito, en la vía respiratoria.
Y en respuesta también un poco, perdona Francisco, las otras dos vacunas tienen más posibilidades de ser producidas. Por lo tanto, creemos por eso que es muy importante seguir con ellas. O sea que también me gustan porque cada una tiene su punto. La producción de una es escalable y realmente nos cuenta que tardó meses en lograr producir a gran escala un plásmido de DNA. Y dices, pero bueno, ¿cómo puede ser eso? ¿No? Para los investigadores nos parece increíble. Bueno, pues tardó meses en lograrlo. Y la otra estaba ya lo tienen instalado para ensayos fase 1 y fase 2, por lo tanto también es muy probable que puedan entrar mucho más rápido, manteniendo la seguridad desde luego. O sea, van a pasar por los ensayos en animales aunque pudiesen empezar con clínicos. Quieren ver lo primero, qué ocurre si hay exacerbación de la enfermedad, etcétera, lo quieren ver. Aunque no todo se ve en los animales, obviamente, pero sí que se puede pasar.
Okay. Interesante. Bueno, estamos un poco tarde. Vamos ha sido buena señal de que hayamos ido tan tiempo. Voy a despedir esto. Si me permite, voy a compartir la pantalla porque antes no pude presentar. My screen was not shared before. So this is the table I tried to show before with the 10 vaccines that are in clinical trials, the different vaccines that are investigating, talking about the anti-vaccination movements, and finally reminding you that we are collaborating with the NGO Africa Alegría Sin Fronteras. Well, I think it's been a productive meeting. We hope to have several safe, effective vaccines soon. Thanks everyone for joining us today. I hope to see you in our future meetings, either online or in person. Thanks all the speakers for your excellent presentations. Well, I hope to see you in the next meeting. I'm going to leave you with a video of our last seminar last November in Almeria. Thanks, everybody. Good luck with your research for everybody. Thank you.
Muchas gracias.
Hasta luego, muchas gracias. Que estén bien. Se cuidan.
Participar.
Chao.